Okay, so I'd like to thank David and Gregory for inviting me to this. I feel a bit of a fraud because I'm not a statistical physicist and I'm not going to talk much about probability or statistics, but some of the stuff I do does have interpretations in that, and it does use differential equations to understand rare events and some stochastic stuff. So, okay, so I'm going to talk about calculation fragmentation processes in sort of starting off with a bit of a review and talk about it in general, and then look at a particular example, this of telomere clustering, telomere clustering and telomere polymer clustering in yeast, which is a topic that David briefly mentioned in his talk earlier in the week. And he's done lots of work on this, so these are the references that I've based some of my work on. So these are stochastic problems, stochastic approaches to the same problem. I'm aware there's a very great literature in calculation fragmentation processes from a statistical point of view, but there's also great literature from a deterministic point of view, and that's what I'm more familiar with, and that's the approach I'm going to take. So it's a bit simpler because it deals with means rather than looking at all the fluctuations, but I can actually solve some of the equations explicitly, so that's sort of quite nice. Okay, so I'm going to start talking about Becker-Doring equations. So these are, with these droplet cluster formations, we're interested in the size distribution of a process. So we're thinking of a system that's got lots of different clusters of different sizes and looking at the distribution of those sizes. So we're going to have a Cj, which is the droplet of size j, or a cluster of size j particles. And in the Becker-Doring model, this can grow or shrink just by one particle at a time. So we have a Cj, which is a big cluster. You could think of it as 10 or 15 or 1,000 or 1,000,000, and it can add or subtract one at each time, at each process. That's a separate event. So there's a flux from clusters of size j to size j plus 1 that's determined by the aggregation rate, the forward rate of this reaction, and also by the backward rate of this reaction. And these reaction rates can depend on the cluster size. So the original model looks at these Cj's as a function of time, and we have the difference of the two fluxes determines whether this concentration grows or decreases. So this system has an equilibrium solution. You can write down, determine these fluxes to be 0. If all these fluxes are balanced backwards and forwards, then you can write down an equilibrium solution that's generated by this partition function, the Qj's, which are determined by the forward and backward rates. So I'm sorry if this is very simple to you. I'm usually talking to mathematicians or biologists where this is quite novel.
Excuse me, is it the same that people call absorption, dissorption?
You could think of this, if you think of this as a large cluster, then when one of these adds to it, it's an absorption, and when it's released, it's a desorption. Yeah. Okay. Any other questions? Please stop me. Okay, so this was written down in 1935. It's a very old model. And one of the first uses was to think about just liquid droplet from a gas. So you've got a gas of individual particles, and now you're growing droplets. So if you draw a liquid droplet, then it's going to have two energies. It's going to have a surface energy due to the difference between the bulk and the surface and the air, and a bulk energy, which we call beta. So if you think of this J as the size, that's the number of clusters, then the bulk volume scales with J, whereas the surface is only going to scale with J to the 2/3. So you have these two competing energies. So if we think of this here, this red curve is this J to the 2/3, which is the surface energy, and this blue is the bulk energy. So this could be grows going linearly, and then the difference between these two is going to give you a potential difference as to how the droplet grows or shrinks. So that's this black curve here, the difference between the two. So you can see we're quite happy to have individual monomers in the gas phase, and then out here we're also quite happy to have large droplets, but there's a nucleation barrier between the two. Yeah. Right. I'm going to talk about both of those later. Yeah. So, yeah. So initially, when Becker and Doring wrote this down, they have monomer fixed. I don't know if that says it anywhere. No. Okay. So at the moment, just thinking about fixed monomer. So there's a fixed concentration of gaseous particles out there. And so if you assume that all the aggregation rates are the same, just one, and you use this Q to determine your fragmentation rates, then you can get this expression for the fragmentation rates, and you can see this only goes from 0.8 to 1.3. It's very slowly varying in J as clusters go from 0 to 100, but you get this huge difference in the partition function.
Sorry, can I just ask
yep.
Q is? Sorry, I missed
so Q is so it's the ratio. If you stick this aggregate, if you assume that the equilibrium solution has this form, QJC1 to the J, and you plug that into here, then and you want 0 fluxes, then the Q's have to satisfy this proportionality, this linear relation between the aggregation and the fragmentation rates. And you need Q1 equal to 1 in order that when you stick J equals 1, this works. C1 is Q1 times C1, the 1. So log Q is like a potential, chemical potential, or it probably has other terms in statistical physics. Yeah. Okay, so it's just, given the aggregation and fragmentation rates, if you fix C1, you can work out what C2 is, and then you can work out what C3 is, and you can work out what C3 is. So you can solve it all successively, and that's just what the... So now it's very important that we're having a fixed monomer concentration. If we fix the monomer concentration, just worry about all the clusters of the other sizes, and we fix the flux to be the same. So this is our equations, our differential equations. So as a mathematician, you look for steady state solutions. So if I want this to be at steady state, the time derivatives to be 0, then all of these fluxes have to be the same. So if I require all of these fluxes to be the same, then this quantity has to be independent of the size. And if that's independent of the size, then I can do this manipulation, divide by this thing, and then some simplification occurs, and then this term becomes exactly the same as, well, this term is the same as this term, but all of these Cj's here, all these J's here become Cj plus 1 here. So now if I sum this term from 1 to infinity, then I've got everything telescopes down and collapses, and all I'm left with is the first term, which is 1, and then the last term. Now if I assume that the concentration of C infinity is 0, then this could be 0. Okay, there's some technical stuff about whether this thing converges or not that we need to worry about, but I'm not a pure mathematician, so I'm not going to worry about that too much at the moment. So if I sum this series, then this right-hand side all collapses, and I'm left with this term here. So this gives me a flux J, because this J is the same for all little j's, so I could take this outside the front, and I end up with this nucleation flux, which depends on all of these AJs, QJs, and C1 to the J's. So if we plot this, what's inside this sum here, we have this curve here, which is this very tall barrier, and this is our nucleation barrier, and the area under this gives us our nucleation flux. So this is typically a very small quantity, and there's a correction factor, so basically it depends on this height here, which is the nucleation barrier, which is this, and then if you do some detailed asymptotics around the peak of this to take account of the width of the peak and the curvature at the top, then you can get this Zeldovich factor, which is a name we've heard already, this term and you can get this more accurate expression for the nucleation flux. So that's a very old classical result, which gives you a rare event, the rate at which some rare event happens depending on the surface and the bulk energies of these cluster growths. So this is fairly standard in some. Okay, so I thought it was just an interesting aside on how Becker-Doring equations can give you this rate at which rare events happen. But that's all been known for many years in parts of the literature. And as a mathematician, I'd call this thing a Lyapunov function. A statistical physicist, you'd probably call it a free energy. And this is some quantity, V, which is perhaps like a Helmholtz free energy, and it depends on all the concentrations, so it's actually a function of time, but it depends implicitly on all the concentrations, and this as a mathematician, it's nice because it tells you that whatever initial state you start in, you're going to tend to the equilibrium solution. So as Gleb pointed out, there are two formulations of the Becker-Doring. The one we've been talking about so far has had the concentration of monomers, C1, to be constant. But there's a more useful one in a lot of applications where you allow the monomer concentration to vary over time. And what you specify is that the total amount of stuff in the system, the total mass, so each Cj is a cluster of J particles. So if we weight that with J, that gives us the amount of stuff in each cluster of size J. And if you add all of that up, then this gives you the total amount of stuff in the system. And that should be conserved. And that's a much more useful equation to impose. So with this formulation, then you end up with a much more complicated equation for the monomer concentration, which couples everything together and makes it all nonlinear. So it's much more hard to analyze mathematically, but is much more useful. This is nice because it still has a Lyapunov function or a free energy. It's slightly different. This has got this C1 here. This doesn't. So this still guarantees convergence to an equilibrium solution. So one of the things I have to point out to mathematicians are quite happy setting the time derivative equal to 0 and thinking that's an equilibrium solution. But as a physicist, you'll be more, and I have to explain to mathematicians the difference between a steady state and an equilibrium. But I think that's probably familiar to most of you, that if we set all the Cj's, all the J's to constant, we end up with a whole family of steady state solutions here. So any J you pick will give you a steady state solution, will satisfy that the time derivatives are 0, but that's not the same as saying that these fluxes are all 0, which is a more precise condition which guarantees an equilibrium solution. So the equilibrium solution is a very special type of steady state. And this constant mass formulation of Becker-Doring only has an equilibrium solution. It doesn't have steady state solutions, whereas the C1 has steady states as well as equilibrium solutions. So sorry if I'm stating the obvious, but it's better to be clear. Okay, so that's one type of coagulation fragmentation process. Another sort is this Smolachowski coagulation fragmentation process, where we allow clusters of any particular sizes to merge. So we can have a size 4 and size 7, or a size 1500 and 3000 can all merge and fragment. So this is a much more complicated process. The fluxes depend on both cluster sizes, and we have aggregation and fragmentation rates which depend on both cluster sizes, and when they fragment, what the two fragments are going to be. And so we have a similar kinetic equation for how these concentrations changes. And again, we could think about this as a constant mass system. The total amount of stuff would be expected to be preserved. And by fixing these aggregation and fragmentation rates in the right way, we can have an equilibrium solution generated by this partition function as we did before. I'll talk about that more in a minute. So when Smolachowski wrote this down, he was just thinking about the aggregation rates, not the fragmentation, and so there's quite a lot of literature on this pure aggregation Smolachowski form, because this allows similarity solutions of this form, G of t, function of J of h of t. So this would be a self-similar cluster distribution size, and if you have constant mass, then the G and the h have to be related by this, and typically you get these similarity solutions. And these G and h functions depend on what the aggregation rates are. And you don't just get these nice similarity solutions. There are 3 special cases where you can actually write down exact explicit solutions. So if all the aggregation rates are the same, then you get one type of solution. If the aggregation rates depend on the sum of the cluster sizes of the clusters combining, you get this form. And if it's the product of the rates, then you get this form. This is a very weird system that it has this gelation property where, although you think that the total mass in the system ought to be conserved, it's not, because this allows very large clusters to aggregate at a very fast rate. And so you get this runaway process where you get an accelerating size of clusters that merge, and eventually you get the loss of mass to the form of a supercluster. You get sort of a single cluster of infinitely large size which forms after a certain time. So in this case, gelation time is 1, so you get a normal size distribution as you'd expect up to time t equals 1, and then you get this simpler size where all the concentrations decay like 1 over t. So the mass goes down like 1 over t, but you can plug this into the equations and it satisfies them all. So there's been quite a lot of work on that. For what we're interested in, we're going to go back to this reversible Smolachowski case, and there the aggregation and fragmentation rates have to satisfy some very special relations if you're going to have an equilibrium solution. So if you want an equilibrium solution where the forward and the backward fluxes match, then you can determine what the partition function is just by knowing what all the forward rates are and just the B1Js. Yeah, so if you define all the B1Js, where it just loses one cluster at a time, and you know all the forward rates, then you can work out what your equilibrium solution is. And then if you want your equilibrium solution to be valid for all of the other B2Js and B3Js, then you need a consistency condition between the aggregation and the fragmentation rates. And so you have to have this condition in order to get a sensible, detailed, balanced solution. Okay, so there's quite a large literature on this. This is a review paper that I wrote a few years ago. If this doesn't hold, then you can still end up solving the systems of equations, but you get a sort of cycling of mass. So you might get the growth of the clusters up to a certain size, and then they fragment into smaller ones. But you need an energy input into the system in order to keep that going. So that could be useful in some engineering processes where you're processing some material and you're constantly feeding energy in. That system might work. Or in a biological system where some cell is providing energy to a process, this might be sensible. But in general, if you've got some passive system which is just relaxing to equilibrium, you'd expect this detailed balance condition to hold. Okay. So that's a review on the theory. Now I'm going to talk about one particular example where telomeres cluster in yeast. So all cells have a nucleus. Well, nearly all cells have a nucleus, and inside the nucleus is the DNA, and the DNA is not just one long strand, it's typically into lots of shorter strands called chromosomes. So these chromosomes exist, and they contain all the DNA that's useful for your genetic code, and the tails of the chromosomes, the end points of the chromosomes, typically contain junk DNA, which is just some sequence of 6 or 8 codes, which keeps repeating. So this is junk DNA that's not particularly important. And it's these telomeres at the end that we're interested in this particular example. It's these telomeres that are clustered together in some yeast cells. So here's just the cell nucleus, and here are these DNA strands, and the end bits are these telomeres. And these chromosomes come up, and they're held at their midpoints at a point called the centromere. And then each chromosome has 2 ends, 2 telomeres. And these telomeres can bind protein particles, and then the protein particles make them sticky, and then they form these bundles, these clusters of telomeres together. Okay, so that's a very crude picture of what's happening and what we're going to try and describe using these coagulation fragmentation processes. So there's 2 stages to this process that I want to model. The first stage is where you just think about one telomere, or the telomeres don't interact with each other. We've got some telomeres and we've got lots of proteins to get in the solution, and the proteins are binding to the telomere to form these clusters of proteins on the surface of the telomere. And this is a reversible process, so they can bind and they can be released. There's a little bit of cooperativity in this, in that if you've just got a single protein on its own, it's not very stable and is likely to fly off. So we're going to have quite a fast fragmentation rate for when this one particle is on the telomere to it being released and fragmented into this free protein and the free telomere. But once you've got quite a lot, then they're going to bind and form larger clusters of proteins on the telomere. So that's our first model, and then later we're going to talk about a more complicated model where we've already got these telomere protein clusters, these complexes, and then they're going to bind to each other because these proteins have made them sticky, and so we form proper telomere-telomere clusters. So that would be a later model. So I'm going to start off with this binding of protein clusters to the telomere. So we're going to modify the Becker-Doring process. So we're going to think of Ci being a telomere with I proteins attached to it, and then one more protein could be added to it to form a Ci plus 1, or this could be released to form from a Ci plus 1 back to a Ci. So this is very similar to, but instead of having C1 here, we've got a P, so it's a separate protein. And so we can write down some equations which look very similar to our Becker-Doring equations. We've got Ci, sorry, I've gone from I to J here. But each one is going to interact with the cluster size above and below, and the flux is going to be dependent on the free protein. So P is the free protein that's still available in the solution to bind, and this is a reversible process. Okay, we're not going to allow things to go up to infinity. We're going to have a maximum cluster size, Cs. So once a telomere has got S lots of the protein on it, then it can't get to S plus 1. So we're going to have a maximum size, so we don't have to worry about things not converging as the size goes to infinity. We've got a slightly different equation for J0 because we've got this cooperativity where clusters of size 1 are very likely to fragment back into C0s. And so this system, we expect to conserve the total amount of protein in the system, which is the free protein plus all the protein that's bound to telomeres. But we also expect it to conserve the total amount of telomeres. So we've got 2 conserved quantities here, not 1. So that's different to the Becker-Doring system. And as well as all the CJs, we can have an equation for our protein, free protein concentration, which depends on all of these other fluxes. Okay. So in this case, rough estimates and parameters, as there are 1,500 proteins, 32 telomeres, have a very crude guess of, say, about 200 proteins could fit on one telomere, although we'll see that they can't all. So this gives us roughly about 50 proteins. We'd expect about 50 proteins to fit on each telomere on average. So these are very large numbers. So as a mathematician, what I'd like to do is do some asymptotics and say this is very big, this is sort of big. So if we had epsilon as about 0.03, about 1 in 30, then this tau, if we scaled t with this, we'd end up with a tau, which is 1. And if we divide this, then this is not, if we divide this by 30, we still get 50, which is a big number. So I'm going to scale the proteins with epsilon squared. So epsilon is a small parameter, 1 over epsilon is big. We're going to say this is big, p is very big, and s is just big, normal size. So sigma, tau, and rho are our order 1 parameters. We'll assume A and B are A is order 1, so that's just a time scale. B will determine later so that the distribution is spread across the whole spread. So we end up with quite a wide spread of distribution sizes. So if we plug those crude estimates into a numerical code and solve our differential equations, we get this. We're going to start off with just free protein and free telomeres and watch our distribution evolve. So all of these clusters go size from 0 to 200. 10 to the minus 5, so we're starting off with nothing bound, and as time progresses, 10 to the minus 4, 10 to the minus 3, we see this distribution form and move across to larger cluster sizes, and then at about 10 to the minus 2, it seems to stop there and decrease in size and spread out and broaden, and then across larger times, it continues to spread out and broaden and changes from this humped distribution into an exponentially decaying distribution. Okay, so we can actually understand these from our differential equations. If we epsilon is about 1/30th, so epsilon squared is about 10 to the minus 3, so this is the first interesting time scale. If we look at very small times, t is epsilon squared, then our protein is still going to be very large, very high concentration of free protein. Then we can plug these scaled versions into our differential equations, and we get rid of the fragmentation. So at this stage, there's so much free protein, it's all binding down, we can ignore the fragmentation process, and we end up with a simpler system of equations, which by doing this change of time scale, sort of implicit change of time scale, we haven't worked out what P of t is yet, but if we assume we knew it, we could linearize the system. So this is hard because it's non-linear, because we don't know the p's and we don't know the c's, and then both multiplied together. But after we've done this, it becomes linear, you can solve it. This is a trick that people have seen before, it's been in the literature. We get this weird distribution, which is like a skewed bell curve. And at large times, it changes from this skewed curve into a more symmetric Gaussian distribution. There's then a second time scale. So this is like a boundary. So this is like a boundary layer inside this boundary layer. And on this time scale, the protein is still very small. Very large. There's still lots of protein, and we can solve this now for how the distribution of proteins changes. If we plug that into the protein equation, then we get lots of terms cancelled because they're higher order in epsilon. This is an order 1 term, which balances this, and so we can work out that the protein is going to decrease. Sorry, I've got the wrong initial condition in there. Oh no, that's right. Sorry, that might not be right. I did this slide last night in the rush. So we can spot how the this should just be rho e to the minus at tor over t2. This 1 minus shouldn't be there at all. But this one's correct. So this free protein concentration is driving the distribution, and as that changes, we can work out this is a conserved quantity, but this changes, this increases, and this has this form. So we can work out how the distribution of cluster sizes changes as well. Like we did before, we can put our assumed form into this. There's still no fragmentation because the protein concentration is so large. We can solve this system of equations. This is now our equation for how the distribution changes. And if we look near the mean, so if we take m1 over m0, the first moment over the 0th moment, this gives us the mean cluster size. And if we look for, this is like fluctuations around that mean, the fluctuations are going to be size root epsilon, 1 over root epsilon. And then if we look for that distribution and plug this form into here, we can convert this from a system of differential ODEs that couple together into a single PDE. We get this, which is a classic diffusion problem. So this is going to continue having our Gaussian distribution, but this is a time-dependent diffusivity in front of it. So this is going to reduce, as our free protein reduces, the rate at which the spread of this distribution occurs slows down. So it continues to broaden, but at a slower and slower rate as time goes on. So that's explaining what's happening in this size, that this distribution is moving across, and we know where it's going to be, and we can know how fat it's going to be, how wide it's going to be. So these fast timescales end either when the protein runs out, which is what happens in our case, or if you had lots more protein there, this distribution might continue going right to the right-hand edge. So it might keep going until it reaches the right-hand edge, in which case we get a different distribution. So we've done the beginning of the process. If we look at the end of the process, we might want to know what's the equilibrium solution going to be. We saw from the numerical simulations this exponentially decaying solution. So we could look for that exponentially decaying solution and try and work out how tall it is and what the rate of decay is. This ends up being quite a tricky problem. You can formulate it quite easily because you've got these two quantities, this C1, which we don't know, and this theta, which is the free protein, scaled free protein concentration, which we don't know. So we've got two unknown quantities, and we've got these two conserved quantities. So you just plug these two unknowns into the two conserved quantities and try and solve them, which leads to a problem that you can't solve analytically, but we can find one equation here. So we can find the C1 if we knew what theta was, and if we knew then we need to plug this into the other equation to find out what theta is. And again, it's going to be asymptotically close to 1, but we don't know whether it's just above or just below 1. But we can plot it and see. So here's this distribution. We want to know this fraction, F, which is the total amount of protein divided by the total space for protein on all of the telomeres. So this is total free protein. S is the total amount of protein that can be on each telomere. T is the number of telomeres. So this fraction is going to be between 0 and 1. And depending on whether it's above or below a half, this is going to be above or below, theta is going to be above or below 1, and it's going to be scaled by epsilon again. So in actual fact, this number's about a quarter. So if we plot this, we want about a quarter, which is about here. So you want this to be about -4, -3.6. And these scales here are, so this is the same picture here, this fraction against this y, which is y is eta sigma. So eta is what we're trying to find, and sigma is the scaled capacity of the telomere. And then these other curves are the 1 and 2 standard deviations above and below the mean. So you can see as you transition from y being negative to positive, the standard deviation blows up and becomes very large and then shrinks again. So depending on how much protein you've got in your system, you can have a whole range of solutions from exponentially decaying to exponentially growing. And the exponentially growing ones aren't a problem because we've got a finite system size. And sorry, this is a picture stolen from one of Dave's papers, but it illustrates that even at equilibrium, the thing isn't stationary. These clusters are continually forming and reforming. The proteins are continually binding and unbinding. There's the rate at which that happens. So at equilibrium, what we'd like to also know, we can take a step back from equilibrium and think about slightly earlier times. How does the system get to equilibrium? So we can linearize around our equilibrium state, introduce a small parameter delta, we expect things to decay exponentially, so e to the minus lambda t. And so this phi j is the shape of the distribution as it's changing to equilibrium, and lambda is the time scale over which it occurs. So what we're trying to do now is find out what lambda is to find out the time scale at which this process equilibrates. Okay, so we can plug this into our conserved quantities and plug it into the general equations and end up with equations for these phi j and psi, these sort of eigenfunctions, and try and work out what the eigenvalue lambda is. So we can solve this system, and after we've applied all the boundary conditions and everything, we find out this lambda is also dependent on epsilon. It goes like epsilon squared, and so our final approach to equilibrium is going to be on the 1 over epsilon squared timescale, so it's going to be very slow. So that's interesting as to whether you would actually see in the living cell, where there's all sorts of other things going on, whether it would actually have time to reach equilibrium or not. So I mentioned earlier this system has a free energy. If you plot the free energy over this solution, you see this interesting plot. So it starts off at time t equals 0 to about 10 to the 4. We see this decay over time scales of about 10 to the minus 2, and then a plateau, and then it decreases again over this 10 to the plus 2 or 10 to the plus 3. So this is our final approach towards equilibrium, which is the final timescale we've just seen, where lambda was epsilon squared. So the approach was t to the the timescale was epsilon to the minus 2, and then this is our initial times. So we've got a change in free energy over these sorts of times where the distribution is moving. Then when it's fattening out, there's no change in free energy, and then the final approach to equilibrium, when it's changing from this Gaussian to exponential, we get another drop in free energy. So I thought it was interesting to point out. I'm not sure what it means, whether it means anything scientifically or not. Okay, so I said the second model we'd look at is a telomere-telomere clustering. So I just point out the model and then show some results, but I haven't developed much theory on this at the moment. So here, I'm going to generalize our Smoluchevsky system from just thinking about cluster size to having two components, two pieces of information about each cluster. So Cij is going to be a cluster of I polymers and J telomeres. So you'd expect a cluster to be 3 or 4 telomeres, or might be 6 or 7 or 12, and then it's going to have I polymers, so that might be a few hundred. So we're going to have lots. So this is a very detailed description of each cluster, and then one of these clusters might merge with another cluster to form a much bigger cluster, and so you'd expect the I's to merge, and the I and R, the total number of polymers to be added, and the total number of telomeres to be added. So although we've got two components, we can still write down our fluxes. This should be a Wijrs flux, but we can write down a system of equations for this. They are a bit scary, so I won't show them. So we're interested in our domain. What I's and J's are we going to allow? So we've got a C10 down here, C10, which is pure protein, and a C01, which is a pure telomere. But then they generally can form clusters, so you might have a C4100 of 4 telomeres and 100 protein particles. We're not going to allow clusters down here because they've got too many proteins for one telomere. So you're not going to have a C1500, one telomere with 1500 proteins on it. And similarly, you're not going to have stuff up here that has lots of telomeres clustered together with no proteins on. So we're just going to have this strange shaped domain in the middle that we're interested in. We are going to allow all the clusters to telomere together, and we could have all the protein bound to clusters like that. So we've got this strange shaped domain with pure telomere and pure proteins. Okay, because we've got fluxes just like we had before, we can write down equilibrium solutions just like we had before. If you balance the forward and backward fluxes, you'd expect them to depend on theta to the I and phi to the j. We want to know what k is, what this amplitude is, how this depends on theta and phi. So you can plug this in to these two conserved quantities, because we still amount the total of telomeres to be conserved and the total amount of protein to be conserved. And if you plug all of this in, then we expect these thetas to be close to 1, because we want distributions which are slowly changing in all of that, in the total number of telomeres and the total amount of protein. We could do some asymptotics like we did before. We expect our I is very large, so if we scale it with epsilon squared, we're going to get an order 1 quantity describing how much protein is on in a cluster. And a telomere, we've got lots of telomeres, so if we scale that with epsilon to the power 1, then we get the total amount of telomere, scaled amount of telomere in each cluster. And then in order to get this distribution to be slowly varying, we want our fragmentation rate to be small. And if we plug that in, then we can get crude approximations to how these mu and nu things change. So we plug this and that into here, and we find out equations that relate the total amount of protein to mu and nu. So it's mu and nu that we're trying to find, which describe the distribution in terms of how much protein and telomere there are. And in this very simple case, we made quite a lot of approximations. You can get explicit results out. So this distribution would be like this. It's fairly boring, but it's a sort of two-dimensional distribution. So you'd expect to have this sort of amount of protein and telomeres, and the distribution decays in both protein and in telomere size. But formally, this sort of model could have all the other types of distributions. So you could get distributions that increase in protein and decrease in telomeres, or you could get a distribution which decreases in the amount of protein and increases in telomeres, and for completeness, the case where the distribution increases with the amount of protein and telomeres. So this is the case where you get a supercluster, all the telomeres and all the proteins in one big blob, typically. And because we're in this asymptotic case where these theta and phis are slightly below or slightly above 1, it's quite delicate that you wouldn't take a big change to go from one of these distributions into the other case. So we're sort of quite close to a bifurcation point where you make a significant change in the qualitative behavior of the system. Okay, so it'd be nice to solve some simulations of this system, but unfortunately with 1,500 proteins and 32 telomeres, I have 50,000 ODEs in my system, my computer wouldn't solve that. So I scaled it down to to just 100 proteins and 8 telomeres, and ended up with 800 ODEs, which I could solve. And so this is the equilibrium distribution that I found, and some time courses. So here we're starting off with free protein and free telomeres, and as they bind, they form this distribution along a sort of line down the middle of the distribution, and then as time progresses further, this fattens out in the other direction towards its equilibrium size. So it's similar to what we saw in the 1D case, where you get this change, and then at later times you get a fattening or broadening of the distribution towards this exponential equilibrium shape. And the telomere and polymer proteins follow these time courses. And we get a similar trace for the Lyapunov function, the free energy. We get an initial quite a sort of early time drop in it, and then hardly any plateau at all, but a slight change in curvature, and then a longer time scale reached to equilibrium. Okay, so I'm running out of time, so there's just one sort of comment which, while I was doing this work, sort of triggered in the back of my mind as to, given any particular system, if you've got some data, how would you know whether it was Becker-Doring or Smolachevsky that you should be using? And so something I'd like to be interested in is to look at systems where you perhaps have it dominated by Becker-Doring processes but have a small amount of Smolachevsky dynamics going on as well. So dominated by cluster monomer interactions but have some other general size distribution aggregation as well. Okay, so I think I'm sort of out of time. Reviewed the deterministic coagulation fragmentation models. I know there's lots of stochastic stuff out there as well. I don't feel qualified to review all the stochastic stuff, but I'm aware of it. I've applied simple deterministic models to this protein telomere clustering in yeast, looking at binding of multiple proteins to telomeres. We see this very broad distribution of timescales. So we see a very early timescale where T is the dynamics are on an epsilon squared timescale, and then right through to very late dynamics when it's epsilon to the -2 timescales, where the exponential the distribution broadens to this exponential case. And the parameters that we got seem to be quite close to this sort of bifurcation where you could change from an exponentially decreasing to an exponentially increasing distribution. And then we generalized the Smolachevsky system to 2 components, these CIJs, to look at telomere clusterings, and then what would be interesting is to look at other problems parameterizing this work or introducing more complicated models. But I think the advantage of this is that you can do so much of it explicitly and look at the results analytically. So thank you very much for your attention. I'm happy to answer questions. Yeah, it probably is important, but oh, sorry. So the question is that I've ignored the spatial diffusion of the clusters. It probably is important in the later time. So it wouldn't change. So my gut instinct is that it wouldn't change the early times, but it might change the late times quite a lot. It would be very easy to include diffusion and say to do a spatial model and just have everything diffusing at the same rate. But I think that's just as invalid. To do it properly, you ought to have the diffusion rate dependent on the cluster size, and then it becomes a very, very difficult problem. You could do some sort of early sort of intermediates where you allow the monomers, small particles, to diffuse with a fast rate and hold all the larger clusters stationary, which would be more, or let them have a very small diffusion rate. But I think you ought to have this change in diffusivities at different sizes to be accurate, if accuracy is what you want to do. But then you can't really do anything much analytically, so you have to do it all numerically. You're right.
In the introduction, you talked about the relatively simple version of the model where you have indeed absorption desorption of a single monomer at a time.
Yep.
And then you only mentioned the equilibrium.
Yep.
You said that there are no steady states, but there is equilibrium. And you didn't mention how this equilibrium is approached when the relatively large clusters, clusters of all sizes, compete for a small number of remaining monomers. And this stage is, it's also a very classic stage.
Yeah.
I'm sure you know it. It's post-fold ripening.
Yeah. Yep.
And the sort of leading order theory coming from exactly these equations is Lifshitz-Lyottov model for the post-fold ripening.
Yep.
So my question is there anything reminiscent of these in the telomere problem, where there is already a very small number of remaining building blocks, and there is still a redistribution of material between clusters? Or it completely lost because you allow for, I would say, absorption of multiple monomers in a single act. Am I making sense at all with my question?
Yeah, you're making a lot of sense. So the nucleation problem I described has this nucleation barrier, and that the solution we developed is a non-equilibrium steady state, because the fluxes are all non-zero. They have this small nucleation. So the point of that Becker drawing is that it's out of equilibrium.
So the nucleation continues until the end. This is what you're saying.
In that case, because you're having this constant input of monos, in that case there's no mass conservation. In the later stuff there is a mass conservation, and there is this there's this competition, but because everything is reversible, there is a release of monomers from the clusters as well. Yeah.
When the clusters are large, the larger the cluster is, the harder it's
Yeah.
the monomer.
I think that's an interesting, difficult problem, because you have this nucleation barrier, and you're considering competition of things either side of the nucleation barrier. In the models, the simple models I've proposed, there isn't a nucleation barrier.
The nucleation barrier for the Austin ripening process just becomes not very relevant, because the number of monomers is so small that they cannot form a cluster themselves, so that the resulting dynamics is essentially competition between big clusters.
I think so.
Why is it different here?
I don't know. I'm aware of this Lifshitz-Lyottov also writing stuff, but I'm not an expert in it, so I don't know the fine details, the technicalities. I'm sorry. What sort of experimental data would you use to verify it? So I haven't got as far as doing that. I'm aware there is some of this size distribution data, but I think it is slightly compromised in that you can't see the smallest clusters.
So actually, just to come back to that question, so there is data, we published a paper in 2012 and 2013 in the biology literature where we had team up with some experiments where they did actually experiments to look at clusters, to look at the distribution of clusters, and employees when you multiply by 2. And so this, now I wanted to ask you the question. So it seems that when you increase by 2, you have a factor 2 in your system. So what they see experimentally is that it switches. You have a bifurcation from, let's say, an average 8 cluster, which contain 4 elements in average, where everything is dynamic, as you mentioned, to one big cluster.
Mm-hmm.
And we could not explain this. Okay. While you are showing, I mean, in the last part of the talk, that you are probably at this bifurcation limit where you can go from one cluster to one cluster. So maybe you could look at this paper,
yep,
where we had this phenomenology we did at that time, some little analysis and some simulation, but we could not get to this bifurcation, to this change when you multiply by 2 the number of elements.
okay, yeah.
Okay, let's thank our speaker again.
Okay, so first I would like to thank the organizers for invitation to this very nice meeting. Okay, so I'll talk about energy current fluctuations in one. Yeah. Okay. Okay, so I'll talk about energy current fluctuations in one-dimensional systems. So this is work done with all these people. Anupam and Sanjeev are here, so initially I was talking to planning to talk mostly about this paper that recently appeared. So yesterday we heard about the fastest PRL, and this work is a kind of a very, actually it's we submitted this paper in 2015, so I think many of you have heard about this work. So I thought I will give a more broad talk. I'll also talk about this, but I'll also talk about our other interesting results in related to energy current fluctuations in one-dimensional systems. Okay, so so basically this is the outline of the talk. So I'll give some introduction to like this question of large deviation functions with respect related to heat transfer, and then I'll talk of two kind of situations. One is like I look at a system which is connected to heat reservoirs, and then look at energy current fluctuations in such a system. So that's the first part of the talk, and then I'll talk about energy current fluctuations in a closed system, or basically I'm on a ring, and then I'll look at current fluctuations. Okay. So these are the two kind of questions that we'll look at. Okay, so so what is the basic question? So let's say we have some Hamiltonian system which has some like a set of particles with some interactions, and we connect it to heat reservoirs at the boundaries. Okay, so then there's a heat current, and let's say we are in a steady state, so there's a constant current going through the system, but now we measure the current, the total current that goes across, let's say, any section in a given amount of time. Okay, so this is so J of t is the current going per unit time across some section, and then we integrate it over time and look at the total heat current that has gone. Okay, so the mean heat current is of course Q by tau. Now this Q of course is a fluctuating variable, so these baths are usually, the heat baths are usually stochastic systems. So so this the heat transferred in a given amount of time is a stochastic variable, and one is interested in the distribution of this P of Q. Okay, so then what one knows is that if we are looking at the heat transfer in a large time tau, then this distribution has a large deviation form, where this it scales with time in this way, and this some function h of q. So q is total heat divided by the time, so it has this particular scaling form, and this function h of q is called the large deviation function for this particular process. Okay, so instead of p of q, one can look at the cumulant generating function, and given this has this form, this cumulant generating function will have this large deviation form. So some mu of lambda into tau, and then you might have a sort of subleading correction g of lambda. Okay, so this h of q and mu of lambda are of course directly related, and mu of lambda in particular, if you expand in powers of lambda, it basically gives you all the cumulants of current. Okay, so so that's called the cumulant generating function. Okay, so usually h of q and mu of lambda are related by just a Legendre transformation. Sometimes this doesn't work if mu of this function g of lambda has some singularities and so on, then this Legendre transformation may not work. Okay, so now so why are these things interesting? So some reasons why these are interesting are, so this function, this large deviation function it satisfies this sort of fluctuation theorem symmetries. So basically if I ask like what is, so I take a small, let's say some system, and I ask what is the probability some q amount of heat got transferred versus what is the probability that a negative amount of heat got transferred against the temperature gradient. Okay, so it turns out that these are related. I mean, so there's you're trying to relate probabilities of like more probable to more rare events, and you find that these probabilities are related by in this fashion. So h of q minus h of minus q is delta beta, which is the temperature difference times the heat current. Okay, and so you can either write it in the symmetry can be expressed either for the large deviation function or the cumulant generating function. Okay, so this is it's nice because it's a general result proof for many systems and valid in like the far from equilibrium regime. If you if I look at small delta beta, then these relations automatically give me linear response relations such as Green-Kubo and Onsager, and then it also gives relations between nonlinear response functions. Okay, then of course the large deviation function is interesting because it tells us what is the probability of rare events, and then given the cumulant generating function, you know all current cumulants, and that's something that one can measure in experiments, and it basically gives some more information about the kind of noise that you have in the system. Okay, so I'll start with so I mean what are the systems where we can sort of actually compute this object, the large deviation function. So one simple example is a harmonic chain. So let's say we have, this is a system, Hamiltonian system described by a quadratic Hamiltonian. So there's kinetic energy, then there's some on-site springs at each site, and then there's some interparticle coupling, quadratic. And then at the ends, this first particle is coupled to a heat bath at some temperature TL, and the last particle is coupled to a heat bath at temperature TR. So, and this one simple way to model these heat baths would be just to write Langevin equations. Okay, so so this is the set of equations by which my system evolves, and then if eventually it will reach a steady state, right? And then we are interested in various questions like what is the heat current, what is the temperature profile in the system, and so on. And then we want to ask what is the if I ask the current fluctuations in this system. Yeah. These coupling terms? No, they are like completely microscopic. Temperature is defined only at the ends, right? And then of course I can find like after the system evolves and reaches a steady state, then if I look at the mean kinetic energy, that will define kind of the local temperature in the system. And then there is some expectation of some other operator will give me the local current going through the system. Okay, so now, I mean, how do you solve this problem? So this is of course a linear system, and you can write a Fokker-Planck equation. And because it's a linear system, you know that the steady state has to be a quadratic, just a Gaussian form. So let's say U includes all the position and momentum of all the degrees of freedom. Then we know that it's going to be some general Gaussian, the steady state, and then basically you need to find this correlation matrix. In the steady state. Okay, so this correlation matrix satisfies a linear equation, and so one way to solve is to solve this linear equation, and this was done in this paper in 1967 for a perfectly ordered harmonic chain. Okay, so ordered means all masses are equal, all spring constants are equal, and then you can actually solve all these correlations explicitly. And okay, so then what you find is that this system has, like, if you look at the temperature, it's completely flat, even though at the boundaries you have some temperatures. And then the other interesting thing you find is that the heat current is completely independent of like how long a chain you take. Okay, so it's completely ballistic transport, which is not surprising because there is no scattering of phonons in this system. Okay, so this is one way you could solve this problem. The other way that you could, again, because it's a linear system, the other way is that if you are just interested in steady state properties, you can just take like Fourier transforms. So this is a linear set of equations, and one can just do Fourier transforms, and then you write the solution, and one can again compute all correlations explicitly. Okay. So if you do this in particular for the heat current, so the heat current is basically like, if I just it's the force between springs times the velocity of it. It's just the rate at which work is done by a particle on its neighbor. Okay. So that's the heat current flowing in the system. And this is again, if I solve the Langevin equation by Fourier transform, I can evaluate it from the properties of the noise. Okay, and then you find that the heat current is actually given by some nice formula, which involves like basically, so the temperature is just appears here, it's just the difference of the two temperatures at the two ends, and then there's a like something like a phonon transmission function, which basically tells me that if I send phonons at some frequency, what is the what fraction is transmitted. Okay. So it's a very simple physical formula, and this transmission coefficient can be computed in terms of the like the phonon Green's function of the system. Okay, so okay, so now so this is the average current that's going through the system in the steady state, and now we are interested in what are the fluctuations of this object. Right. So okay. So now we look at this object. Let's say this is the integrated current. So what is this? So this is the force from the left reservoir on the first particle, right? Minus gamma v plus eta. That's the Langevin noise. And then this is the velocity of the first particle. So this is really the heat current that is going from the left reservoir into the system, and then I integrate it over some time tau. So that's the total current that's flowing into the system. Okay. So this is of course a functional of the noise and the stochastic variables, and then we want to compute this distribution. I mean the cumulative generating function corresponding to this object. Okay, so again this problem one can do it by two approaches. One approach would be to write a joint distribution function for the probability that the system is in some phase space point, and the fact that it's the total amount of time the heat transferred is q. So one can write a joint like a kind of a extended Fokker-Planck equation for this joint distribution, and then one can try to solve that equation. Okay. So basically one can define a generating function which is conditioned on the initial position of the system and the final phase space position, and then this quantity basically satisfies some Fokker-Planck equation. Okay, so the first method would be to so this is I mean it's called some tilted generator, and so you get a sort of master equation for this joint distribution, and then you need to just find the largest eigenvalue that gives you the cumulative generating function of in this system. Okay, and from the eigenvector you can actually compute the leading correction. Okay, so this method is kind of difficult. Because this generator is kind of complicated. So if you have just one particle connected to two baths, you can probably compute this, but beyond that it's difficult to find the spectrum of this operator. Okay, so again what we figured out is that since it's a linear system, you can again work out things just using Fourier transforms. Okay, so this is kind of an old paper where Anupam and Sanjeev and so we use this just the Langevin equation approach, and again you find that this entire cumulative generating function can be expressed just in terms of the same transmission coefficient for phonons. Okay. So, so you basically get an expression like this. I mean, so basically it's because it's all the main idea is that the energy current is quadratic in the noise, and then you can just use the fact that the noise has some distribution and you can compute this. Okay, so that's the main trick that we use. Okay, so this is the cumulant generating function. So it's logarithmic of this factor here. So there's the transmission function here. This is the temperature, the left and right, and this delta beta is just inverse of this temperature difference. Okay. So now from this, what can you do? You can, of course, if you expand this, then the mean is just given by the earlier expression we had for the steady state current, and then you can obtain like fluctuations and so on. And you can check that this Calavati coherent symmetry is satisfied and so on. Okay, so this actually one can also do it in the quantum case, and using our approach we could also compute the leading correction G of lambda. Okay, so this result can also be extended to like the three-dimensional system connected to heat reservoirs at the boundaries. Okay, so now some comments about so we are finally interested in the cumulants. So what do you learn about cumulants from this expression? So okay, so we have an explicit formula. If you expand in lambda, you get all cumulants, and so for n equal to 1, this just gives the average current, and from the formula what you see is that okay, so here the main point is this: if it's a perfectly ordered system, then this transmission coefficient for large system size kind of becomes independent of system size. Okay, so the transmission doesn't decay with system size. So all these cumulants basically become independent of system size. Okay, so if it's a ordered harmonic crystal, then there's no, I mean, all cumulants are independent of system size. Okay, so that's ballistic transport. And okay, and so this statement is true also for when you if it, I mean, it's still connected to reservoirs, but they are at the same temperature. Okay, so it's an open system but at the same temperature. In that case, all the odd cumulants vanish, but the even cumulants are non-vanishing, and they have this sort of ballistic property that they are independent of how big a system you take. Okay, so this is for so I mean, this formula of course is if all the mass, if it's a perfectly ordered crystal, then this is a ballistic system. But if you make the masses like random, or the spring constants random, then it's a disordered system, and you can, for example, you can also get diffusive transport in this system. Okay, so then of course this transmission coefficient would decay with system size, and if it's diffusive, it would decay as 1 over n. So, so even that is that kind of property is also included in this system model. Yeah.
Distribution of P of Q.
Yeah.
How does it look like? Does it look like a Gaussian, or I mean, tail or something?
I mean, the middle is of course Gaussian, but the tails are usually like exponential.
Details from your
Sorry. Okay, so for some simple, like if you take some, like let's say 2 particles or something, then you can get the tails explicitly. I mean, you can, but in general, I think they're just exponential. Is that right, Sanjeev? I think the tails are usually exponential. Okay, so okay, so this formula you can also use basically if you have a 3D disordered crystal, you can try to understand like diffusive transport and how do cumulants look for a diffusive system. Okay, so okay, so now the question is what about current fluctuations in a diffusive system and systems with anomalous heat transport. Okay, so I'll try to explain what is anomalous heat transport, but first let's look at the more common kind of systems which show diffusive heat transport. What can we say about current fluctuations? Okay, so in such systems, I mean, there's a very general formalism using a conjecture due to Boudinot and Derrida called the additivity principle. So if you have a basically it I mean, so there's the additivity principle basically says that when you have this the large deviation function can be kind of constructed by looking at the large deviation function of by some extremizing the large deviation function of addition of like 2 parts. Okay, so there's some prescription which I won't explain, but basically I'll just try to explain the final result that you get from this prescription, which is valid for diffusive systems. Okay, so I mean, so basically what you can using this principle, it gives you an explicit formula for the cumulant generating function, which just involves two functions. Okay, so one is the thermal conductivity as a function of temperature, and the other conductivity is the current fluctuation as a function of temperature. Okay, so the current fluctuation is just defined as, like, if I take a system in like a system which is connected to reservoirs at equal temperature, and then I look at the second second cumulant. That defines the current fluctuation, and then it's of course will be a function of temperature. Okay, so I need to know these two functions of temperature, the diffusivity and the current fluctuation, and given these two quantities I can compute like the entire cumulant generating function. Okay, so it's explicitly given by some formula like this, and so here I have this kappa of t and sigma of t, which are known functions. And then finally I want it as a function of lambda, and so this lambda is like parametrically determined by this second equation. Okay, so therefore I mean this is a completely explicit formula, and only thing I need to know about a system is its temperature dependent thermal conductivity and this fluctuation. Okay, so this is quite a remarkable result, and it has been shown to produce exactly known current cumulants up to several orders of for the symmetric exclusion process, for which there is an exact computation, and then it has been numerically verified for this KMP model, which is a stochastic model of heat conduction, and then we also tested this formula for this disordered 3D harmonic crystal, for which we have an independent formula, right? So we found that this formula still works. Okay, and now for one thing that we note is that this formula predicts that all cumulants actually scale with as 1 over n. Okay, so the current, of course, in a diffusive system, the current scales as 1 over n, but all cumulants also have the same scaling with system size. Okay, so now I'll talk about systems with anomalous heat transport, and okay, so the what is anomalous heat transport? So if you take any one-dimensional non-integrable momentum conserving Hamiltonian system, you typically find that Fourier's law of heat conduction is not valid, and this is anomalous heat transport. So some of the signatures of anomalous transport are that the thermal conductivity is not finite, it diverges with system size, and if you put a heat pulse, it spreads, it doesn't spread diffusively but spreads super diffusively, and you find that temperature profiles in the system are always nonlinear, even when the temperature difference is very small. Okay, and then you also find this anomalous current fluctuations, which I'll now talk about. Okay, so there's a very detailed theory of now anomalous transport using nonlinear fluctuating hydrodynamics, which has been developed by Herbert Spohn for the last few years. This is like there was some earlier work by Ramaswamy and Anupam and Henk Peijeren. Okay, so let me just explain what are the main ideas of fluctuating hydrodynamics. So okay, so the main idea is that if I take a system in equilibrium, and then I ask what is the form of equilibrium correlation functions. Okay, so basically if I take a system in equilibrium and I perturb it, like I just dump in some energy at some point, then what I'll find is in these systems is that like there's a part which spreads kind of slowly, and then there are some part which is carried by sound modes. Okay, so there are sound modes in the system, and then there is heat mode. Okay, so and the prediction of this theory is this tells us like how does the heat mode decay and how do the sound modes decay. Okay, so that's the prediction from this theory, and it tells that the sound mode actually has is related to the KPZ this Kardar-Parisi-Zhang function, and I mean so this is the prediction that the sound modes satisfy this kind of scaling, and the heat mode has a Levy scaling. Okay, so basically when I dump in energy, I'll find that there's some part which evolves like a Levy distribution, and then there are these two some part where the heat is being carried by the sound modes, and those sound modes are moving ballistically with some speed, the sound speed, and then they are spreading with KPZ scaling. Okay, so this theory also you can compute the heat current autocorrelation, and you find a slow decay, which explains why you have diverging thermal conductivity in this system. Okay, and this theory also tells us that there are actually two universality classes in the system. One which is described by this, where the sound modes are KPZ and the heat mode is Levy, and there is a second universality class where the sound modes are diffusive and the heat mode is a Levy with a different power. Okay, so this is Levy 5/3 and this is Levy 3/2. Okay, I hope this is clear. Okay, so I'll just show some experimental simulation results on testing this theory. So this is what I said, like if I perturb a system at this is simulations of a Fermi-Pasta-Ulam chain, which is a nonlinear chain with some cubic and quartic nonlinearity, and I prepare it in equilibrium, and then I perturb at the origin and I see how the perturbation spreads, and then you see that there are this slowly spreading peak at the center, and then there is this peaks which travel at the speed of sound, right? And the prediction I said was this should have Levy scaling, and this peaks should have KPZ scaling, and this is what you find. So if you scale, do the appropriate scaling, you find indeed that you get a collapse to the KPZ scaling function for the sound modes, and for the heat mode you find a collapse to the Levy distribution. Okay. So here I have plotted the Levy distribution and the KPZ scaling function, and you can see very good agreement. And the theory actually also predicts this scaling parameters, and at least in some cases you find very good agreement. This is not always true.
They don't match.
Sorry?
They don't match somehow.
No, it matches, right?
I don't know.
No, where do you say it?
Match. I mean the heat mode and the Levy mode. I mean because the Levy has a tail and the KPZ.
Oh, you're trying is asking whether you can have a single scaling like.
Yes.
No, I mean they of course connect. I mean this guy is connected, but it's you can't like do the kind of analysis that you would.
Make the large division tails of this central part to match with the Levy.
So this it's a Levy distribution, but it gets cut off at at some finite, like the speed of sound into time. No, so it because I mean it doesn't beyond c into t it it's cut off by the sound speed. I mean, and these peaks occur exactly at that okay. Right. Okay. So now from this picture of energy transport in from hydrodynamics, one comes up with this sort of phenomenological model for heat transport, where you think of the heat is basically carried by. So what we see is that it's super diffusive, the spreading of heat. So we try to model it by assuming that the heat is carried by particles which are doing a Levy walk instead of a random walk. Okay, so so these are the main features of that I mentioned, and then it's clear that the heat carriers are not doing a simple random walk, and so then there's this picture of that has been developed for some time, that heat transport is by Levy walkers. Okay, so what is the precise model? Okay, I have 10 minutes. 10 minutes is it? Okay. Okay, so maybe I'll speed up a bit. Okay, so let me just explain the Levy walkers model. So basically now we think of this, I mean you can think of like this, there are these phonons and they are basically carrying the heat, but they are doing a Levy walk, and so the definition is basically each you choose a time tau from some power law distribution, and then you choose a direction randomly. So the velocity is plus minus 1, and then you move in a direction for a time tau, right? So this is different from Levy flight, and so you choose a power law distribution which has a finite mean and infinite variance. And okay, so given this basic model for the Levy walk, one finds that you can reproduce many of the anomalous features that I discussed here. Okay, so I won't go into the details. So one, like for example, you can reproduce this temperature profile. So if you take a heat bath where you have some finite density of Levy-Walkers at the two ends, then you find that the temperature, the density profile of the Levy-Walk has this singularities at the ends, which is same as the temperature profile that you would see in a Fermi-Pasteur-Ulam chain. Okay, so so this is one thing, and then you find that the current scales with system size as with some exponent, which is related to the power law in the for the Levy flight distribution. And so just with that single parameter in the Levy flight distribution, you can explain a large number of features like the temperature profile, the current dependence on system size, and also we'll see that you can also understand fluctuations. Okay, so if you want to understand in this model I have the bath of Levy-Walkers, and then I have the system, like what is the fluctuations in the current going through the system. Then if I am looking at large time tau, then it's basically it's like a Poisson process. So to compute this object, you can just do some simple Poisson statistics, and this gives the large deviation function for heat transfer completely. Okay. Okay, so now with this Levy-Walkers model, again we have the large deviation function for heat transfer, and this again tells us that all cumulants will have the same scaling as the current. Okay, so all of them scale anomalously with system size, and this explains some observations in for hard particle gases. Okay, so now finally I'll talk about the energy current cumulants on the ring geometry. Okay, so far I talked about these properties of the cumulants on the open geometry where I had reservoirs, but now we look at the system where it's a ring which is prepared in thermal equilibrium, and then we measure the same quantity and look at its fluctuations. Okay. So this was first looked at by these people in 2010, and their main finding was this. Okay, so the system they looked at is the something called the alternate mass hard particle gas. So you have like a set of point particles with the masses m1, m2, m1, m2. So if it is equal masses, it's an integrable system, but as soon as you make the masses different, they become non-integrable, and it has good mixing properties. So it had and then it's known that this is a system with anomalous heat transport, and the thermal conductivity has the same divergent exponent as the Fermi-Pasteur-Ulam chain. Okay, so their main results are they looked at this current cumulants for large tau, and they found that the second cumulant actually scales as 1 over L to the power half, while the fourth cumulant scales as L to the power half. Okay, so this is completely different from the open geometry where you find that all cumulants have the same scaling with system size. Okay, so here somehow the fourth cumulant has large fluctuation and shows much larger fluctuations than the second cumulant. Okay, and for a diffusive system, what is known is that the second cumulant scales as 1 over L, and all higher cumulants scale as 1 over L square. Okay, so this I said already, and okay, so now we wanted to understand this from this Levy-Walkers model, and again we use the same model, and let me try to explain how you can try to compute these fluctuations from this model. Okay.
So
Yeah.
I got confused. So you were on a ring. So
Yeah.
how do you get a temperature gradient?
No, there is no temperature. It's a system in thermal equilibrium.
How do you get a current then?
No, so there is no average current, but then if you look at a point, there is some there are fluctuations right all the time. So yeah, so you just look on an average it's 0, but you have on the even on the if you have particles, right? On an average you have 0, but then you can look at the fluctuations in the current, like on exclusion process or something. Okay, so now. So how do we calculate this current fluctuations? So basically on this ring we have n independent Levy-Walkers, and they are moving on this ring, and Okay, so then if I look at a single walker, then let's say it has done some displacement x of t in time t, right? Then the number of times that it goes around the ring is just xt by L. Okay, so it's on a finite ring, so it this is the number of times it goes around the ring. So therefore, the total this q to the power n, I mean the fluctuations is basically given by this to the power n, and then the average, and then the total number of walkers. Okay, so these are just independent walkers, so the total is just given by n times this. Okay, so now this is given by this, and for the Levy walk, of course, we know that if you take second cumulant, it's faster than t, and if you take nth cumulant, it's of course it's much faster than t. Okay, so which is not good, because we want the cumulants to scale with time. Okay, so now so what we now know is that this Levy walkers actually on a finite ring, they will the Levy walkers will have a finite lifetime, and I mean you can't have infinite tails, okay, because so I'll explain the reason later, but what you expect is that this Levy distribution should have a cutoff which depends on the system size as L to the power delta. Okay, so therefore you introduce a Levy walk which has a power law tail, but then with a cutoff at some time determined by the system size. Okay, so L to the power delta, where I'll try to explain where this delta comes from. Okay, now given this cutoff, then one can just use the Levy walk model and compute all these cumulants, and you get a form like this. Okay, and now what is the cutoff? So I said there are these two universality classes. In one case, the sound mode is KPZ has KPZ scaling. In the other model, the sound mode has diffusive scaling. So for the case where the sound mode is diffusive KPZ, there you expect that the relaxation time should scale as L to the power 3 by 2. Okay, so this is just the time at which the sound modes would decay if you have a finite system. Okay, so this is one relaxation time, and in the other case you have L square, and so this gives you the value of delta that you should use in this formula for the two systems, and once you have delta, and then the other parameter is the power law decay, which you know from the heat conduction exponent, and so then you can make predictions for this all the cumulants for these two universality classes. Okay, so then what you find is that C2, C4, and then these were already measured, and you get the expected you get the what the observed results, and then C6 is this. Okay, this is the sixth cumulant, and for the second model you get a completely different scaling. Okay, so I'll just show the numerical results. Okay, so for the hard particle gas, I mean so we computed these cumulants, and you find that the second cumulant has this 1 over n to the power half scaling. The fourth cumulant is n to the power half, and then the sixth cumulant has this n to the power 3 by 2 scaling. Okay, and for the for this other so there is this model called momentum exchange model, where it's a stochastic model, but which is in the other universality class, and there you find that the cumulants are completely different. Okay, so right, yeah. So maybe I'll just give my conclusions, and then if I have time, I'll try to explain this cutoff, which I didn't hear. So basically, I talked about large deviations in this equilibrium energy current fluctuations, and I tried to argue that using this Levy walk picture, you can completely understand the system size dependent exponents, and then I discussed these connections to this KPZ model. So the main results are that the current fluctuations are large in systems with anomalous transport, and so there are these two universality classes for anomalous heat transport. In one model, you find that you get this scaling of various cumulants in this way, and in the other model, you get a completely different scaling. And this can be compared with systems, diffusive systems, which where you would get this sort of scaling. Okay. And from our this is completely explained by this Levy-Walk model, and in fact all cumulants are predicted. Okay, and then this is other thing I want to point out is this is very different from the cumulants that you'd get if you took a system and connected them to reservoirs at the same temperature. Okay, in which case all cumulants would scale in the same way with system size. Okay, then there are some results on I mean the some combination of these cumulants are supposed to be universal, and this is something we tried to check numerically, and while it's kind of close to the expected new universal value, it's not completely verified. Okay, so I'll stop here. Okay, so it's universal with respect to like I mean like whatever the coupling constants and models, yeah, even independent of like whether hard particle gas or FPU chain. So the powers are of course universal, but the prefactors are not universal. But then if you take these combinations, it's supposed to be completely universal.
Are there any more questions for Abhishek?
Yeah.
You mentioned here the alternating mass model and momentum exchange.
Right. Yeah.
Does it also fit with the FPU models? I mean, what can you say there?
For the current fluctuations, okay.
Example, yeah.
Okay, so I mean somehow okay, right? Yeah. So this I mean, see, these current cumulants are numerically extremely hard to determine. Okay, so here you can see for this exchange model, we could really go to really small, very small systems, and for this alternate mass, this is something like this. So we also did FPU, and there somehow we couldn't it's even some we don't understand why exactly, but the numeric, I mean, we don't see anything very clearly. Both alpha beta model, right? Yeah.
So is there some understanding for why there is this relation between the sound and the heat modes? I mean, why for the KPZ sound mode you get one Levy heat mode and for the diffusive you get another, or is that just an observation that these come together?
No, so like when you so basically when you do this fluctuating hydrodynamics, what you find is that the so you have these three conserved quantities, and then you write the hydrodynamic equations, and then you write the equations for the modes. So the let's say the sound mode, I mean basically okay, so I mean, so there's basically there's some okay. So in general, the in the hydrodynamic equations, you get some nonlinear terms like this. So the sound mode couples with the other modes. So I mean, and then this coupling parameters are determined by the microscopic theory. So in one case, the special case, this it just happens that this mode okay, sorry, no, what am I saying? Okay, yeah. So the coupling to the heat mode couples to the okay. So in both the cases, the heat mode couples to the sound modes. Okay, so the coupling is basically so there are these two sound modes, and this is the form of the coupling to the sound modes. Now in the so in the for the KPZ case, the sound modes basically satisfy the sort of a Burgers equation. Okay, and in the other case, the sound mode satisfies just the diffusion equation, because the coupling parameter is 0. I mean, so then it just satisfies plain diffusion. I mean, there's no correction to the and then it feeds into this equation. And so because in one case it's diffusive, so it gives you this 3/2 scale Levy, and in the other case it gives you the
Okay, if there's no more questions, we'll finish up there and reconvene at 11:30, and thank Abhishek again.
Thank you, Martin.
I managed to get a cold yesterday from air condition, so I'm sorry my voice have changed, but I will try to go through anyway. So like this? Okay. I will try to turn it off if I sneeze my nose. Okay, thank you very much, David and Gregory, and for the invitation. It's always nice to come back to Italy and to meet all of you. So thank you. Today, given the subject of the conference, I have decided to show you some things we have been working recently on anomalous diffusion. My work in all the things I will show you, it's an epsilon. The true work has been performed by these people, particularly by Lamberto Rondoni and Jürgen Vollmer. And well, so let me start about what anomalous diffusion is. It was mentioned just before by Abhishek. So most of you know, in many experiments, you are interested in study transport properties of the system, and one of the things that characterizes that transport is the mean square displacement, right? And when the mean square displacement usually scales in time with some power nu, and if this power nu is not, if this dependence is not linear in time, then one speaks of anomalous diffusion for such process x of t. Even though, even in situations where you find anomalous diffusion, you can always define a generalized diffusion coefficient in terms of the variance of the displacement with this particular scaling. And if the speeds are bounded in the systems, then usually, well, then this power scaling, it's defined, it takes values between 0 and 2. Then when it is less than 1, you say you have a subdiffusive transport. Diffusive is nu equals 1, and superdiffusive is nu, it's between 1 and 2. There are more complex situations which can be studied if you look at the power scaling or the scaling in time of higher moments of, in this case, the displacement. One can, for instance, think of higher moments, or the displacement moment of order q that scales in time with some function of q, right? I write this dependence this way, such that for nu q equals 1, then you recover diffusion, but it is not particularly important how you write it down. It's just convenient to write it this way. And so if you have such a situation and nu q is not 1, then you say that your system shows weak anomalous diffusion. Weak in contraposition with what will be strong anomalous diffusion that I will show you. So this case is when nu q is not equal to 1, but still it is constant, right? So the dependence that you have on the power scaling is linear in q, right? Because nu q is constant in that case. There are, in such a case, it means that the whole distribution of the displacement evolves in time. I mean, the evolution of the distribution of displacement is characterized by a single scaling parameter that can always be written in this way, right? So you know how the maximum of the most probable value of the distribution, the amplitude of the distribution behaves in time, and how the spreading is around its center.
What's the difference between weak anomalous and anomalous?
Yes, I'm just arriving at strong anomalous. So weak anomalous diffusion is when this parameter nu q, it's constant. It does not depend on q itself, right? So then in that case, you have a linear dependence of this. It will be some constant times q. Although it is not 1, it is constant, right? And so weak, this surname weak was added to anomalous diffusion because there are other situations which are characterized not by one single scaling, but by several ones, right? In that case, what you will see is that nu q is not constant. It is a function of q itself, such that this, the exponent appearing here is a nonlinear function on q. Okay, right? So nu q has adds a dependence on q that makes this nonlinear, right? And in such situation is what you call strong anomalous diffusion. Okay. If you have, for instance, in the case in which you have not one but two scalings for the probability distribution of the displacement, then usually these two scales appear at different time scales. I mean, processes that are determined by the center, by the bulk of the distribution, that might in general be weak anomalous diffusion or diffusion itself, and also rare events, rare excursions, that even though they are rare, they are long-lasting, and that are determined by the tails of the distribution, right? So in such a situation, when you have two different behaviors for the bulk and the tails, usually you expect to have a piecewise linear function of q times nu q. Okay? So this strong anomalous behavior appears in several examples, several experiments of biological and physical background. Some of them were mentioned by Eli in his talk. Here I will show you some examples which are mathematical examples and to model different transport processes that exhibit this strong anomalous diffusion. And the first example, it's a paradigmatic example, one of the most simplest cases in which, even though the dynamics of the model itself are very easy, are integrable, exactly solvable somehow, but integrable, the properties of transports are very complex. Let me explain to you in what sense. So let's consider, this is a billiard, so let's consider a polygonal channel billiard, which is made of identical cells, and each cell is made by a polygon in the upper wall and another polygon in the lower wall, right? And so to study transport in this cell, it means to follow the trajectory of a particle, point particle, that exerts specular reflections on the walls of this channel. Now, if you repeat this structure, then you get an infinitely long polygonal channel. The walls are linear. There is no defocusing after the hit in the walls, and therefore there is no exponential separation of nearby trajectories. Therefore, there is no chaos. I mean, this is a completely integrable system to transport, right? Now, the parameters, there are these 4 parameters, because the walls can be either parallel or unparallel, opening or closing. So this h, for instance, and delta x determine the roughness and the horizon of the billiard. The horizon meaning whether you may have infinitely long trajectories of the particle or not. And delta yt, delta yb for top and bottom determines the focusing of the trajectories. Nevertheless, as I say, the focusing is a linear separation, not exponential. So dynamics is fully integrable. And then the question is what the transport properties of a density of particles inside this very simple channel are. This was studied several years ago by Lamberto and Owen Jeffs, who was a postdoc of him at that time, and also a very nice work by Hernán Larralde and David Sanders in Mexico. So let me show you some cases. Let me start for the case in which the walls the upper and lower walls are parallel, right? This situation. So in this situation, delta yt, delta yb are the same, so the walls are parallel, and then h simply tells you how separated they are. If h is larger than the sum of these two, delta yb, delta yt, then there will be an opening, horizontal opening, in which trajectories may travel for very, 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 very long distances, right? So in that case, the horizon is infinite, and trajectories move ballistically, to very long distances. But this is not the case here. And even though this is not the case, so that you don't have any, let's say, infinite trajectories being ballistic, what you observe if you measure the mean square displacement for such a situation is super diffusion, and a super diffusion that scales, an MSD which scales as t to the power 5/3. This is an observation. It is funny to observe super diffusion in these systems. There should be some sort of, you may guess, some sort of persistence of particles moving for very, 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 very long distances to the right or to the left, and this is the origin. These geometrical sort of correlations of such a channel are responsible for this anomalous super diffusion, right? Yes?
What is the motion of the particle inside?
So particle is free flight. Yes, it's a billiard, right? You have one particle, and there's free flight, and then it bounces specularly in the walls. Initial condition will be uniform on the unit cell. This cell, you may start initial condition here, and then you see how this, which is random, yes, which is uniform in number, yes. Constant speed, yes. Sorry. All this means, when I say billiard, it means all those things, but yes. Sorry. No, it is a numerical result. It is an observation. But it's a numerical observation that is, you will understand why. You won't be surprised this is not analytical result, because imagine now that I consider a billiard, which is a channel which it does not have parallel walls, but almost parallel walls, right? Imagine that delta y, delta t is not this, but this plus epsilon. Then what you observe for the mean square displacement is written here. So for when the walls are parallel, this is here h is fixed, so there is finite horizon. When the walls are parallel, you get this 5/3, but for very little variation of the parallel of the walls, you get subdiffusion, as a matter of fact. So you don't see superdiffusion, you see subdiffusion, and then if you continue making the walls less and less parallel, but this is still a small variation, then there is a strong dependence on the power scaling of mean square displacement. So it is an awful system, so to say.
Go down again at 0.35.
Yes, and then it goes up. These are these are numerical results, power scaling of mean square displacement. So most of you know when you do numerics that you are never sure whether if you wait longer, you see longer trajectories, this exponent will change. So it's if you don't have a theory, it's a delicate affair. But Owen Jebs this very careful numerics, and apparently this is the situation. But even though it's this is non-linear, non-monotonic behavior, the striking observation here is the fact that this sort of complexity or the properties of the transport are very singular, right? For parallel walls that you may judge as a special case of the billiard, you get superdiffusion with this exponent, and if you go off an epsilon, then you see a completely different behavior, right? And if you consider the same ratios of delta yb, delta yt, but then you change the delta x, the width of the of the central cell, of the cells, sorry, like in the case in which delta yt divided by delta x is 2, in this case it was 1, but in this case it's 2, then you observe another exponents, right? So you see superdiffusion again when they are parallel. In this case, probably horizon is open. I don't remember. Maybe. It's not important for what I will say next. And then you see a whole bunch of parameters for which you may have some sort of diffusion of the particles inside the channel, right? So the exponent, the mean square displacement grows linearly in time.
For one, there is no horizon. There is no infinite horizon.
Yes.
For one.
Yes. Yes. For 2 it won't be neither because h is fixed. So yes, these are, thank you, these are both cases with closed horizon, right? So this is the situation, and as I say, I mean, even though it's a striking or surprising, nice, simple Villar model, if you look at the transport is very complex. It has a greater unpredictability because of all these singularities of the transport properties, even more than what you would expect of a chaotic system. This is, on the other hand, not surprising because, as I say, the dynamics are integrable, and we all know that, I mean, in integrable dynamics, while trajectories are more ordered or stable, the structure of phase space is very, very unstable upon changes of the parameters. They don't have this stability that a chaotic system have. Okay? Yes? Yeah. No, the shape is the same. So the shape is this one, right? And it is only repeated and repeated and repeated. Infinitely repetition of this is not unit cell, but this, how you call it, basic cell. Okay, let me show you some examples of trajectories of this model. No? For instance, this is the position along this infinite chain of polygonal billiards. This polygonal channel. You start at the central cell, and then as time passes, you start seeing these trajectories. Of course, if you look closer, then you see there are reflections of going from different walls. These are, I mean, if the cells are of width more or less 1, of order 1, then you see that the trajectory goes pretty far from the center. This is one realization, one trajectory. And then you will see, well, yeah, as a matter of fact, dynamics is very simple. You have these oscillations going down. It's like effectively being ballistic with some delays due to the this is the position of a particle as a function of time. Sorry. Yeah? So you start at the central cell, and then it does, for that specific initial condition, then it does this trajectory. So you may say, okay, this is perfectly boring, right? But then you go to longer times, and what it was, what you observed before, it was this. And then, but then something happens, it makes a change, a reflection that takes this motion back to negative values of the channel, and then again, and then again, and again. So it's, again, boring behavior, but something you didn't expect it if you look at this very short time, right? We continue going to longer times. You may say this has ended like this, but this is not the case. So you have this, and then all of a sudden you have a very long trajectory going in one direction, and then these repetitions, and then a very long trajectory, and then these repetitions, and so it's very complex. And I have a fourth plot, one. This is taken from this paper, which is again it changes. right? So you have what you have before here is there, before in the previous one is here, and then you have these very long excursions and structures that appear. And of course it will continue happening. So it's, you know, it's not boring, it's a very simple model. Still transport, it is complex, and this singularity on how transport is very difficult to, you know, from a theoretical point of view, maybe it's not achievable. But one of the things that you may see is that you have this sort of excursions along the channel, which looks like, from a global perspective, looks like ballistic behavior. So trying to understand this, I mean, the reason why they studied this thing was to study transport of non-interacting particles and how the walls, the interactions with the walls affect the diffusion. But then to try to explain this, Lamberto came out with an idea which is he thought of an exactly integrable map, exactly solvable model which is integrable, that has more or less the same properties as what happens with the polygonal billiard. So he thought, okay, if you have in the polygonal billiard, this separation of trajectories happen. I mean, this complexity should, I mean, arises because of the tips of the channel, right? Because these tips are the only ones that may separate trajectories, so all complexity should come from that. Even though it's linear, the complexity should come from that. So if you have a bundle of initial conditions here, these trajectories will do something, while these will do something else, and these others will do something else. So there is, like in a Cantor set or Baker map, or there is separation of trajectories that in this case are linear. So the map is this, is defined in this way. So you have a unit interval that has two slicers. The slicers give the name to the map. Right? So you have the unit interval 0, 1. This is 1/2, and then you have two slicers. One slicer which is L, let's say L0 here, and the other which is symmetric, so it's 1 minus L0 of positions. And then you have you uniformly fill the interval with initial conditions, and those that are at the left are moved to the same interval but one unit to the left. Those that are at the right, between 1/2 and L0, are moved to the right. And here, those that are at the left are moved to the left, and those that are at the right are moved to the right. Okay? So this is what the map does. You can see an example here. So it starts dividing the initially uniform density of particles in different directions. And globally, what this map shows is so times grow like this. So they are either advanced by one unit to the left or to the right, until and the slicers, and the slicers do also depend on time, which is not exactly this m, but it's the you can take m as the time. So the slicers are also moving in the interval, right? So a trajectory which is here, or to 1/2, a trajectory which, or let's say here, a trajectory which is here will always go to the left until the slicer changes and it is to the left of the particle. And when that happens, the trajectory enters a period 2 cycle and it starts oscillating forever, right? So it's like in the slicer map, a trajectory will be, if this is time, will be ballistic, and then it will start oscillating and stay there forever. Okay. Nevertheless, the system is, if being the system solvable, you can compute the distribution of displacement and moments and things like that, and it shows, it exhibits subdiffusion, superdiffusion, and normal diffusion depending on this parameter alpha. no? The parameter that tells you how the slicers are evolving in the interval. So one can obtain, for instance, the moment of displacement. I won't show you how, but then you have these different regimes, no? The order Q moment of displacement will either be linear, I mean a scale as Q minus alpha if for higher moments. It has logarithmic corrections if you look at the order alpha exactly, and it will be constant. So this is what you see here. This is a straight line with slope 1 minus alpha. Here is Q equals to alpha, and then it will have a constant. You can choose at 0 as well. Okay. Now, this is essentially what we call a strong anomalous diffusion, right? Because again, you have this piecewise linear or globally nonlinear function or behavior of the power scaling of the moments as a function of the order of the moment itself, right? I skipped this. This is the same figure for the moments of displacement for the case I was showing to you before with parallel walls. And here you have, you don't observe a strong anomalous diffusion for that case. You get Q to the minus 1/3 describes quite well this behavior, but it goes down to 0 or to 1/3, let's say. And for the case, if you move a little bit from parallel, then you see completely different thing. This you see that it will be this subdiffusive. In this case, MSD here it's ballistic, and here it will be subdiffusive, and maybe you see some nonlinear behavior. But nevertheless, for the parallel walls, it's a very special case in which you don't see this strong superdiffusion. So the slicer map mimics that behavior, right? And once I visit Eli in Barilan, I mean, once not, at the beginning of this year, and then we were discussing these results, and he told me, oh, well, look, you have these ideas, this random walk approach, and then essentially I will have to go fast, yes. So, but anyway, this is very simple idea that he already explained, is to heuristically try to obtain how the global distribution function of the displacement scales. So for the slicer map, you see that for short moments, which are those occurring, let's say, shorter times determined by the bulk of the distribution, they are constant, they do not evolve in time. And for linear, they evolve like this, right? So one can think in such a situation of strong anomalous that the bulk of the distribution is characterized by such by an scaling in X, but constant in time. So this theta is time-independent constant, while at details you may have a scaling that generally you may write like this: 1/t to the beta, and a function which is scaling the distances as t to the xi, right? And so for large times, or far from the bulk, this is what you would expect, and all that needs to do is to match these two distributions to obtain the dependence of this difference. Sorry. Of these different parameters. Okay, so if you go to shorter distances, this has to match this other distribution, which is constant in time, and so you fit all these time dependencies, and you find that beta. I mean, first of all, since slicer map is characterized at large times by ballistic events, then you expect that this scaling must satisfy ballistic trajectory. So psi should be equals to 1. And if you match these two, you obtain that beta appearing here should be related to the scaling at the bulk of the distribution as 1 minus nu. No? So you should have something like this for the tail. And for the tail, you may obtain very simply, now that you have a dependence, you may obtain moments which are higher than this nu, and you do the integrals are very easy, and you obtain exactly this linear behavior, p minus nu, q minus alpha, and so on and so on. This is also sort of, this program is related to what Eli was saying of this single big jump principle, in which when you have rare events, the statistics at very large time are characterized by the statistics of a single, the single biggest jump. Anyway, so let me show you another model, which Eli discussed already. So I will pass through over is this Levy-Lorentz gas. No? In the Levy-Lorentz gas, you have a particle that is moving on the line, and it has free flights in between scatterers, and the positions of the scatterers are randomly chosen according to a Levy distribution with parameter alpha. Okay? So when a particle hits a scatterer, then it chooses randomly whether to be transmitted and continue moving to the right, or to be reflected moving to the left, right? So this is the Levy-Lorentz gas, and then Eli introduced it several years ago, and this is an example of the trajectories that you see there. So this is the gray lines show the position of the scatterers. So you see that different realizations do something different, but then there are these very long waiting times when there is a gap of scatterers in which a particle moves ballistically until it does something else, or like this, that does something else and go forward and things like that. So this is more or less what you observe for Levy. For some parameter alpha that I don't remember which one is it for this particular plot. As a tour de force, Rafael and Alessandro, that were here at the beginning of the conference, managed to compute this power scaling, the scaling in time of the mean square displacement, and they found that there are these three different regimes. One regime which is quadratic for this parameter alpha less than 1, then some linear regime for alpha between 3/2 and 1, and then it is diffusive. Mean square transport is diffusive for alphas larger than 1/2, right? And they went through, and they show also that if you look at the arbitrary order of the moments, they are described by these laws, depending on whether alpha is less than 1 or greater than 1, right? And again, for Levy-Lorentz gas, you see a strong anomalous diffusion, right? Now, one of the things you start look at it is that you always see this straight line here of a slope 1, and the reason why it is slope 1 is because the processes are dominated by ballistic transport at larger times. So if this is such a case, one would like, for instance, to try to have a model which is exactly solvable, having exactly the same properties of any other models that may not be as easy to solve as this one, to describe a certain class of systems for which you may have access to the values of all the moments of the distribution of the displacement, and also, since we are interested in talk about transport of the correlation, right? This behavior has been also observed, is also observed in villas with infinite horizon, as Eli showed this as well, right? It irrespective of whether the dynamics is chaotic or integrable. If you have these infinite channels in which a particle may fly for an unbounded distance, then you have this situation, right? This is, for instance, the case of the usual Lorentz gas with regular geometry, and you see that if the horizon is closed, the transport and all moments are characterized by diffusion, which is p half here. This is the order of the moment. But if the horizon, as long as the horizon is infinite, then you have for lower moments, they are diffusive, but starting at the second moment, the mean square displacement, then you have super diffusion, which is given by p to the minus 1. So this is again another type of systems. If you look at different polygonal channels, which are not, which has no parallel walls, you also observe this strong anomalous diffusion. This case h, so these parameters are fixed here, but the important thing is to know that for this h equal 127, this has infinite horizon. So you see that the transition between ballistic and diffusive occurs at the exactly at the second moment, at the mean square displacement. But there are other situations. These are two examples of closed horizon in which this transition occurs at a higher moment. In this case, to the third moment. In this case, in the fourth moment. And one would expect that you have other situations similar to those. So to put all these different examples in context, Jürgen Vollmer thought of an even simpler model than a slicer map, which is the following, which is fly and die dynamics. Fly and die dynamics means that one start from a uniform distribution of initial conditions in the unit interval, and then each initial condition flies for a given time, and then it dies. It stops there, right? So it's very silly, simple dynamics. This is how it goes. It's continuous in time. So at time t, the position of a particle that started at x0 is in the unit interval, moves ballistically for times which are shorter than this tc, and then it remains there for times that are larger than that. So flies and dies. And the times at which each initial condition stops or dies is chosen by this distribution with a long tail, right? So x0 is in the unit interval, and b and xi are simply positive constants. So the nice thing about this is that all countings that you want to do are very simple. Instead, for instance, for compute the moments, instead of integrated with the probability distribution function, you may simply look at the measure at the unit interval, because since everything is determined by the initial condition, then you simply have to solve this, right? So you consider for instance, the probability distribution function of particles that fly for a time larger than t, and obviously this is simply determined by the initial condition for which tc is larger than t, and this is the one. So I take the measure, for instance, at the displacement of order q, the displacement moment of order q at time t will be to integrate over all initial conditions, which are uniform, and we will have these two contributions, those that have that continue flying after time t, and those that have already died, and then you have these two contributions and obtain a very direct, in very few lines, a direct result for the moments, right? So, well, this is special k when q is equal to xi, and again you see this strong anomalous diffusion characterized by this by similar powers than slicer map, okay? So you compare these different two dynamics, and then you realize that to match the mean square displacement, one would need, comparing these two results, one would need to take b equals to 2 and alpha equals to psi, and then the moments of displacement of the slicer map are exactly the same as the moments of displacement for fly and die, at least for those which are higher than alpha. But more surprisingly, and this is the message of what I'm presenting here, is that if you do this matching, then the identity goes beyond the moments. It also goes to the time autocorrelation function for the displacement, which is also important to determine the transport properties. I will show you this in a second. The same happens with the Lévy-Lorentz gas. So I have these analytical results, and I compare now with the Lévy-Lorentz gas, for which I also have access to this estimated result. And then if I make the map of psi characterizing fly and die with alpha characterizing the Lévy-Lorentz gas, then I get exact expression for the moments and also for the correlation. Yes, it seems so. Sorry. Let me. Okay, I'll just show you. Give me just 3 more slides. So these are slicer map, fly and die, and Lévy-Lorentz gas. And then this strong anomalous diffusion would simply means to match the second moment, the mean square displacement, to have a value for the spectrum of the higher moments. And it also works. You can compute for fly and dies also very easily correlation function. I'm sorry I have no time to show you, but I show you the plot for this figure comparing these 2 models with the fly and die, for which I can compute everything very easily. And you see that for a particular scaling that it is written in this form, all 3, once you do a match, the transformation that matches the mean square displacement, the correlation function, the time autocorrelation function also collapses for the different models. The same happens with the Villiers, so you have different polygonal channels, the Lorentz gas, and again, after doing the matching of the mean square displacement, this happens as well. So this motivates us, and I'm finishing now, to define, I mean, maybe it's too pedantic all about a university class, but let's say about the class of systems that are characterized by fly and die class. So if it is defined by any dynamics that is asymptotically dominated by ballistic rare excursions, no? Then the MSD must belong to the ballistic family in the strong anomalous diffusion, but also to the one determined by the bulk of the distribution. And if the autocorrelation function, which unfortunately I didn't have time to show you, admits a certain scaling, then we say that all the systems belongs to the same class. There are other things we are trying to analyze, which is what happens if, for instance, the particles in the Lorentz gas exchange energy with the substrate. In that case, this is simply numeric. You see strong anomalous diffusion, but in a completely different way than what you were seeing before. This is subdiffusive, and one of the things would be to see how one characterizes this strong, or if a strong anomalous diffusion appears for other observables other than displacement. So sorry for the delay, and thank you.
Okay, we've got time for 1 or 2 quick questions for Carlos. Devin.
You replace this polygonal channel with a smooth one, you lose everything, or is it still be anomalous?
Polygonal channel with
some smooth thing like sine wave or something, you know, then you lose this behavior of anomalous. Is it important that you have edges? That's what I.
Well, it is important indeed. Lamberto, I think what they tried was to make the tips rounded, to be able to consider finite size particles, because they were also interested in see how blocking of this particle, interaction between particles. Once you add that, then you have chaos, right? And then everything turns out to be diffusive and as usual. With a sine wall, I have no idea. I have no idea, but this would still be integrable. If you have like a car circuit, race circuit, which is always parallel walls, it will still be integrable, and I have no idea what would happen.
If you have a channel, but you have infinite horizon, and the boundary is chaotic, you still have it. Because then you will go back to the Lorentz gas infinite horizon.
Well, I am.
It's not diffusive.
What is not diffusive?
If you have a channel,
Yes.
you have a different horizon and the scattering is chaotic,
Yes.
you still have stronger amounts of diffusion.
Yes.
If you have a different horizon.
Yes.
When the horizon is not in.
Yes. Yes.
You say it's diffusive, it's not always diffusive. When it's into the horizon, it's not.
I don't remember when I say it is diffusive, but sorry. Yes, sorry. Yes, David, there was a correction to my statement. If you make the tips rounded, but the horizon is infinite, then it will still be super diffusive, not diffusive. Yes, if not, then it is diffusive. Yes. There is one exception to that thing, which is for the parallel wall channel. For the parallel wall channel, you have this 5/3 for the scaling of MSD. That one, no? Well, yes. Okay, this remains the same even if the horizon is infinite. And even if h is very, very, very large compared to the roughness, it remains the same. But that's a very special case, which it's difficult to analyze.
Yeah, for this polygonal billiard channel, so you had this nu versus q, right?
Yes.
Yeah. So does it depend at what time you compute this? Because you showed that in the previous one, the behavior changes very much, right?
No, it does not depend. Of course, you take care of observing that at a very large times,
okay,
but it doesn't change it.
So suppose I just looked at the previous time, like if you had this figure initially, it does.
Yes, I understand why you asked.
Yeah.
The answer is no, it doesn't.
So if I compute it any of this time, I get the same behavior?
Well, maybe not with this time,
okay,
but for these last two, you will get the same. Yes. So there is a convergence too, obviously. I mean, not for the moments, but for this, surely something happens. I mean, what happens in the parallel walls is that the velocity vector, since this is a polygon, has some particular angles, particular directions, and the diffusion of these directions is very, 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 very slow. So when you see a change in this behavior, it's because these velocities have changed such that instead of you cross over a tip and then everything changes. But then you have to wait for this rotation of the velocity vector to pass over another tip again. That's
okay.
Intuitively.
Let's thank Carlos again.
Okay. I'd like to first thank the organizers, David and Gregory, for organizing this wonderful conference and inviting me. And this has been a wonderful week, and in this conference has been wonderful in this wonderful city. Okay, so today I'll talk about extremal statistics in 1D Coulomb gas. So I'll explain what is 1D Coulomb gas and as well as explain extremal statistics. Okay, so this work is done in collaboration with Abhishek, Satya, Sanjeev and Gregory, who all are attending this conference. And these are the references of this talk. Okay, so universality. This is a quite common concept that we encounter in our basic courses in statistical physics, like phase transitions in liquid gas and paramagnet, ferromagnet. So there are other simpler contexts in which you observe universal features. For example, central limit theorem. So let's consider n independent and identically distributed variables chosen from some distribution Px, which have finite moments. So let's these are the variables x1, x2 till xn, and look at the sum of these variables. And in the large n limit, if you properly shift this sum and scale by square root n, then these scale variables, the distribution of the scale variable converges to an uniform universal distribution, which is the Gaussian. It doesn't depend on what is the what Px you choose, as long as it has finite moments. So this is one notion of universality. There is another situation in which one observes universality, which is quite common,
this is extreme value statistics. Once again, consider an independent and identically distributed random variables, which are say x1 to xn, and this time you look at the maximum of these variables and ask what is the probability that this maximum is less than or equal to x. And it turns out that in the large n limit, once again, if you shift and scale by appropriately, which are non-universal constant, which may depend on n, which depends on n actually. And if you look at this variable in the large n, the distribution of this variable in the n going to infinity limit also converges to universal functions. And there are three possible types of these universal functions, depending on the tails of this distribution from which you choose these IID variables, and these distributions are Gumbel, Frese and Weibull. So the question is, what happens if these variables are strongly correlated random variables? So the more precisely, let me ask this question, that given the joint distribution of these n variables, what is the distribution of the maximum of these variables? Whether in the large n limit, do you have a limiting distribution, and if so, whether this limiting distribution is universal? So these kind of questions were addressed in the last few decades in the context of random matrix theory, where one usually considers a random matrix of n cross n size, and the elements of these matrices are random and they are chosen from some joint distribution, and we consider only the Gaussian random matrices, or this joint distribution is Gaussian and in such a form that they are invariant under certain transformations, like orthogonal transformation or unitary transformation or symplectic transformations, and these invariance properties actually define ensembles. So you have Gaussian orthogonal ensemble, Gaussian unitary ensemble or Gaussian symplectic ensemble. So and because these matrices are invariant, the distributions are invariant under such rotations, and in this case one looks at the distributions of the eigenvalues of these matrices, and eigenvalues of these matrices are real, and this is what one is interested. So the distribution of the eigenvalues of these matrices, and the question, the answer to this question was given by Wigner in 1951. He wrote down this elegant formula for the joint distribution of the eigenvalues for these ensembles, Gaussian orthogonal ensemble, GUE and GAC, where you have a parameter beta which takes different values for these different ensembles. And you see that there is a Gaussian part, and you have a part in which reflects the fact that the eigenvalues are interacting. So suppose we have such a joint distribution of eigenvalues, then the question is, what is the distribution of lambda max, which is the largest eigenvalue? Okay. So before going to answer this question, let me tell you the one thing, that there is a nice interpretation of this formula due to Dyson. He says in 1962, he said that, look, this distribution looks like can be interpreted as a Maxwell-Boltzmann distribution of n charges which are living in one dimension, however interacting via two-dimensional Coulomb interaction, which is logarithmic interaction, and confined in a harmonic potential. So this can be interpreted as a gas of such particles in one dimension which are interacting via 2D Coulomb interaction. And we'll call this system, this system is also called in the literature as Coulomb gas, sorry, not Coulomb gas, log gas, or Dyson's gas. Okay, so I'll refer this system and the rest of my talk as log gas. Okay, so let's come back to the question of largest eigenvalue. So this term, this interaction term, this is a Coulomb repulsion term. So this term tries to push the charges apart from each other, whereas this term, this is the confining term, which tries to bring all the charges at the center of the potential. As a result, because of these opposing effects, it turns out that these charges in the larger limit settle down over a finite region, and you can ask what is the average density, or this will be also the typical density in the larger limit, and ask what is the average density of these charges. And Wigner showed that in the n going to infinite limit, this average density also converges to a n independent form, which is basically this semicircle, which is 1 over pi square root 2 minus lambda square. And this is now known as Wigner semicircle law. Okay, so the lambda max, if we are interested in the lambda max, which is the maximum eigenvalue, or in the log gas picture, lambda max is basically the position of the rightmost particle in the gas of charged particles picture. Okay, so the average, on an average, this lambda max will sit at the edge of this charge distribution, of course. So the average is basically square root 2. However, this lambda max is fluctuating around this mean position, and typically it fluctuates on a scale which is of the order of n to the power minus 2/3, where n is the number of such charges on the line. And this can also be seen by looking at the gap at the edge of this distribution, and this is the gap available for this lambda max for the lambda max to do a typical fluctuation. The question is how to describe this the distribution of these typical fluctuations. Okay, and in 1994, these two gentlemen, Harold Widom and Craig Tacey, they gave the answer, and they said that if you subtract the mean and then and scale appropriately, then this distribution in the larger limit approaches to a limiting distribution, which is f of beta, which is now known as residuum distribution. And this distribution is expressed in terms of some solutions of Poisson-Leverrier 2 equation. For example, for beta equal to 2, this solution is explicitly given in terms of this function qy, where qy satisfies this Poisson-Leverrier 2 equation with this boundary condition that in the y going to infinite limit, this function should approach any function. And these are the plots. So for this residuum distribution for different values of beta equal to 1, beta equal to 2, and beta equal to 4. And you observe that this distribution is quite asymmetric on this with respect to right, and if you compare the right and left tails. And indeed, in the right side, the decay, this function decays as e to the power minus z to the power 3/2 as z goes to plus infinity, whereas on the left side it decays much faster compared to the right side. It decays as e to the power minus mod z cube as z goes to minus infinity. You have seen this asymptotics in Alberto's talks. He also had mentioned about this. Okay, so this distribution, the residuum distribution, it describes the typical fluctuation of the lambda max, the position of the rightmost particle. And these typical fluctuations are of order 1 over n to the power 2/3 around this mean value square root 2. What about probabilities of large fluctuations, which are not in this scale but much larger than this scale? So maybe you can consider the fluctuation that the rightmost particle is order 1 distance away from this mean position square root 2, either side, this side or left side or right side. And these questions were studied by Satya, David, and their collaborators, and they showed that the probabilities there can be described by large deviation forms, and these probabilities have large deviation forms. And in the left side, this probability decays as e to the power minus beta. Beta is the parameter, the minus n square with a large deviation function. On the right hand side, it decays as e to the power minus n and a large deviation function. And one can understand these factors n square and n intuitively from the energy scale involved in observing, in creating such rare events. And they have also computed these functions explicitly, and these functions around this mean value root 2, these functions behaves in this fashion. Phi minus goes to 0 with a cubic power, whereas phi plus goes to 0 with a power 3/2. Now these large deviation functions, remember these large deviation functions actually can be obtained from the ratios of partition functions. So as a result, one can think of this, one can associate these large deviation functions as two free energy densities, and this is the distribution. But if you look at the cumulative probability and define as a free energy density, then this free energy density in the larger limit actually becomes this. So which is basically says that this function decays to 0 on the left side with a cubic power, and on the right side it just stays 0. So as a result, if you look at if you keep on taking derivative, you will have a discontinuity at the third derivative, and that you can associate to a third order phase transition as you do usually in equilibrium physics. Okay, so so this is a small summary of this extreme value statistics in log gas. It's basically that the lambda max on an average sits at square root t, and it has typical fluctuations of order n to the power minus 2/3, and which is described, these typical fluctuations are described by Tessier-Ulam distributions for this typical fluctuations. And when you have large fluctuations, then those are described by large deviation, appropriate large deviation functions. Okay. Okay, so this is a kind of summary of log gas, and this Tessier-Ulam distribution has been discovered in the context of largest eigenvalue, the distribution of the largest eigenvalue in the in random matrix theory. However, it has appeared after that in many other situations. For example, in Ulam problem of long-case increasing subsequence, and then in Dhar-Parigi-Zhang equations, in height fluctuations, in stochastic growth models, in non-intersecting Brownian bridges, also in mesoscopic fluctuations of spectrum of quantum gas. When you quantum dots, when you put a quantum dot near a superconductor, there will be a gap, and if you look at the energy spectra near the gap, that gets fluctuations because of the safe fluctuations and the gate voltage fluctuations. And that statistics of this fluctuation is also Tessier-Ulam distribution. Then this Tessier-Ulam distribution is also observed in non-interacting fermions, which are confined in harmonic potential. Not only that, this Tessier-Ulam distribution have also been observed in experiments, in liquid crystal experiments, also in experiments in coupled lasers. So there are two nice popular science articles. One is in Nature Physics and another is in Quantum Mechanics, which actually discusses about this ubiquitous properties of Tessier-Ulam distribution. So it's kind of quite universal. Apart from that, there is another universal aspect of this Tessier-Ulam distribution, which is the following. So remember that we had started with this joint distribution, this log gas, where these charges are confined in an harmonic potential and interacting via this logarithmic repulsive interaction, pairwise logarithmic repulsive interaction. But it turns out that if you replace this confining potential by any arbitrary potential which is sufficiently confining, then also the charges actually settle down over a finite region, and as long as this charge density at the edge near the average lambda max it decays in this fashion, like square root fashion, then the typical fluctuations around this mean value of lambda max is still described by Tessier-Ulam distribution. So this is another universal feature associated to Tessier-Ulam distribution. So so that means if you change the confining potential, then also it in some cases you can describe the typical fluctuation by Tessier-Ulam distribution. So this brings us to ask this question: is it also possible, instead of changing the confining potential, if you change the interaction? So earlier we had considered this interaction, logarithmic interaction, but suppose we keep the confining potential to be harmonic, but change the interaction among the particles and take something else, will the distribution of the lambda max be described by Tessier-Ulam distribution? This is the question. Now to ask this question, you can ask the next question, then what could be the natural candidate? What could be the candidate for a different interaction? Anyway, these charges are living in one dimension, so why not consider the actual 1D Coulomb interaction? So actual 1D Coulomb interaction is mod interaction potential. So we consider this system and ask this question. So in the rest of my talk, I'll refer this system as 1D Coulomb gas and this system as log gas. Okay. So, in this system we look at the distribution of the position of the rightmost particle for this system, and the answer to this question is that it's no, that the typical fluctuation is not described by Tissue-Widom distribution, but there is something else. So, let me first tell you the results, and then I'll tell you about briefly about how to derive those results. Okay, so as you remember, in the log gas case, in the n going to infinite limit, the charges on an average settle down over a semicircular region, over a finite region, and the distribution is basically a semicircle. Here also the charges settle over a finite region minus 2 alpha to 2 alpha. Note that alpha was the strength of the interaction. Okay. So, the charges settle over a finite region, and here in contrast to the log gas, the distribution is flat, not like a semicircle, and lambda max on an average sits at the edge, or x max, which is the position of the rightmost particle, sits at this edge. And here we find that the typical fluctuation of x max around this mean value is of order 1 over n, in contrast to the log gas case where it was of order n to the power minus 2/3. And we ask what is the distribution of this typical fluctuation, and we find that this typical distribution of this typical fluctuation around this mean value is described by a limiting distribution, which is obtained from a solution of a non-local eigenvalue equation, whereas in the log gas case, this limiting distribution, which is the Tissue-Widom distribution, is obtained in terms of the solutions of a Pauli-Lebedev equation. So, this is not described by Tissue-Widom distribution. Okay, so this describes the typical fluctuation. We also have studied the large deviations. So, this describes fluctuations in this scale, which is of order 1 over n. We also have looked at large deviation, the probabilities of large fluctuations, which are of order 1 on about this mean position on this side or that side, and we find that these are also described by appropriate large deviation functions. And in comparison to log gas, here you see that on the left hand side it's e to the power minus n cube and with some with a large deviation function, and on the right side it's e to the power minus n square and a large deviation function. And if you compare with the log gas, you observe that here it's n square and here it's n. So, here also if you define this free energy density as we did in the log gas case, you will see that there will be some phase transition, and this function also actually goes to 0 around this mean position cubically with a power cube. That is why here also you will see third order phase transition. I'll tell you in detail after a few slides. So, this is basically the kind of summary of the results which I wanted to tell you about. So, let me give you tell you briefly how to derive these results. Okay. So, we have this system. This is gas of particles, and which are confined in harmonic potential, and they are living in one dimension, and they are interacting via this 1D Coulomb interaction. And suppose we are interested in the average density or the typical density. So, in the larger limit, this average density will get contributions from the configuration in which this energy is minimized, and this energy function is pretty easy to minimize, and you find out that in the minimum energy configuration, the charges actually sit at equal distances. The position is proportional to the level, and the gap between this particle is basically 2 alpha by n, which is constant. As a result, if you find out the density has to be flat, and you see that the leftmost particle, which is x1, which is at minus 2 alpha in the n going to infinite limit, and the rightmost particle, which is xn, if you put n here, and then it's basically plus 2 alpha. So, the charges actually sit between minus 2 alpha to plus 2 alpha, and their gap is constant. So, the density is flat, which is 1 over 4 alpha. Okay. Now, X max average is 2 alpha, as I said earlier, and then this X max fluctuates around this 2 mean value at order 1 over the fluctuations are of order 1 over n, and this can also be seen easily if you look at the gap between the rightmost particle and the next rightmost particle around this value. The gap available for the rightmost particle for it to fluctuate. You can look at the suppose delta is the gap, so then if you integrate from 2 alpha minus delta to 2 alpha of this density, then within that region you have only one particle. So as a result, this is 1 over n. So and since rho is constant, it's uniform, you can easily see that the delta is of order 1 over n. So the order of the typical fluctuation is order 1 over n. So in analogy with log gas, one can expect that if you subtract the mean and scale by this typical fluctuation, then this scaling variable, so you basically subtract the mean and the scale by the typical fluctuation, this variable in the n going to infinite limit should have an n independent distribution. That is what the scaling distribution, that is what I mean by scaling distribution. So this is what we expect, and we get this distribution, and to compute, how to compute this distribution. Okay, so to compute this distribution, okay, we have to start from this joint distribution, and it is always convenient to compute the cumulative probability that the X max is less than W. That means all the particles are below W, which is like you basically integrate this probability distribution with an infinite barrier placed at position W. So this can be written, you can easily see that it can be written as the ratio of two partition function, where this partition function is restricted, where you have an infinite barrier at W, where this is unrestricted, that means W is at infinity. So you have to compute these partition functions, and once you know this, then if you take the derivative, you get the probability distribution. Okay, so this is the task what we have to do. So basically you have to compute this partition function. So look at the energy expression, and in this energy expression it is easy to see that if you permute the levels of this or permute the positions of these particles, this energy expression is symmetric under the permutation of the positions of this particle. So as a result, one can use this information and one can write down this integral as an ordered integral, which will be n factorial times an ordered integral. So basically you have to perform this integral maintaining this order. And why do we want to do that? Because if we make these variables ordered, then we can lift this modulus, and this becomes just xi minus xj, because anyway they are ordered. And once they are ordered, and this is a quadratic variable and this is a linear variable, we can actually complete the square, and there is a constant which is not important, because anyway you are going to take the ratio. So we can, so basically you can see that this expression was kind of any pair was interacting, but we have converted it to a sum of local terms. Okay, so this is very important. And this structure suggests that we should do a scaling we should do a transformation of the variables from xi to epsilon variables. Basically we take this as the variable, and if we do this transformation, this partition function becomes simpler, and it becomes this constant factors coming from this and that, and another integral which has an argument, and this argument here, note that interestingly we get the right combination of this variable, because this is the combination we wanted in our previously. So this in this combination, so this is the desired scaling variable that we wanted, and this partition function is basically given by this multiple integral. Note that this integral, by doing this trick, we have transformed the problem of computing the partition function of a long range interacting system to the problem of computing the partition function of a short range interacting system. Here the particles are interacting by a short range interaction. So, for example, if you look at this expression, if you put alpha equal to 0, this is basically hardcore gas, no particle can cross each other. But by putting a finite alpha, you are basically relaxing this hardcore interaction by a little bit. So, that means these particles can cross the particle on the right side, but at most by an amount 4 alpha. So, this is a short range interacting gas. And once you have, because once you have a short range interacting gas, there are many things which are known in equilibrium statistical physics. So this is a good simplification. Okay, so we have to finally compute this, and which is the ratio of this partition function, and which becomes the ratio of this partition function of the short range gas, which I call this f alpha. And we still have to compute this function f alpha. And it turns out, if you do some simple calculation, simple manipulation, this function f alpha satisfies a recursive differential equation. And remember that we were interested earlier in this question whether p and x max has a scaling form in the n going to infinity limit. And this is equivalent to asking whether f in x alpha, which is basically this ratio, whether this quantity also has an n independent limiting form in the n going to infinity limit. This is equivalent question, and this is what we want to find out. Note that in this expression the n dependence explicitly comes through this ratio. So this is possible only if in the n going to infinity limit this ratio goes to an n independent constant. Now question is whether this is true, whether in the n going to infinity limit this ratio is really an independent constant or not. As I said earlier, that this is a partition function of a short range interacting gas, and which is basically a soft core interacting gas. And usually in short range interacting gas, we know that the free energy usually are additive. So this should be proportional to n, because this is the partition function of short range interacting gas. So the free energy, if you take the log of this partition function minus log of this partition function, it should be proportional to n, because these are. So if we expect that this should be like e to the power n this function. As a result, if we use this property, then we should expect that in the n going to infinity limit, this ratio should go to an n independent constant. So this is actually true just by using the property of the short range interacting gas in equilibrium. So we know that this constant actually in the n going to infinity limit goes to an independent constant. Let's say this is a alpha, and assume that this function also goes to an independent function. Then we get this equation where we do not know a alpha and also f alpha. We have to solve this equation to know simultaneously to know a alpha and f alpha, and this solution have to satisfy this condition. Why? Because as we have seen that f alpha is actually a cumulative probability. So in x going to infinity limit it should be 1, and x going to minus infinity should be 0, and it should be between 0 and 1 throughout. And also it has to be positive throughout this range, minus infinity to plus infinity. And since it's a cumulative probability, its derivative, which is a probability distribution, it also has to be positive. So we have to solve this equation with these conditions, and we get a alpha and f alpha together. So in that sense, this is a non-local eigenvalue equation, which this is like an eigenvalue which you have to solve, and this is like an eigenfunction. Okay, so this is the problem. Now finding a alpha for any general alpha is usually analytically is usually very hard. One can solve this equation numerically and find out a alpha, and then get f alpha as well. But one can actually find out limits of this eigenvalue. And interestingly, Baxter had encountered a similar problem while computing the partition function of a 1D one component plasma in finite box, and analyzed a similar partition function. And we use his result and find that this eigenvalue diverges when alpha goes to 0 as 1 over 4e alpha, whereas in the alpha going to infinite limit it converges to a constant which is 1 over square root 2 pi. For other values of alpha, we compute this A alpha numerically, and this is the plot. So we see that this numerical evaluation, the points are from exact numerical evaluation, and they are very consistent with this asymptotics quite well. And for each value of alpha, we have A alpha, and for these values of A alpha, we can find out F alpha as well from this numerical solution. And this is the distribution of F alpha, which is the derivative of capital F alpha. And this distribution describes the typical fluctuation of x max at the scale of order 1 over n. Once again, this distribution is also asymmetric like the Tessier-Ulam distribution, because the tails are different. This side it decays as e to the power minus x square, in contrast to the Tessier-Ulam distribution, where in this side it was decaying as e to the minus x to the power 3/2. On the other hand, in the left side, the decay is quite similar to the Tessier-Ulam distribution. This side is decays faster, and it decays as e to the power minus mod x cube in the when you take x going to minus infinity. Okay, so this describes the typical fluctuations, as I said. Now I will talk about the large deviations of this x max, fluctuations of this x max. And as I mentioned earlier, these large probabilities of these large deviations can be described by appropriate large deviation forms. So let me first look at the left side. So we are interested in the probability of this event. So this is the mean position of x max, and it is this typical fluctuations is of this scale. But we want to know the probability of this event where the rightmost particle is at order 1 distance away from 2 alpha on the left side, and this probability will be very, very less, and we want to compute this probability. And of course, we once again look at this partition function and find out the partition function by placing an infinite energy barrier at position W. Now, suppose you have this infinite barrier and you are bringing it from minus infinity. As long as the position of the barrier is above 2 alpha, then these charges in the n going to infinite limit do not feel that there is a barrier, because they are happily sitting between minus 2 alpha to 2 alpha. But as you bring it inside this charge distribution, these charges will rearrange themselves, because they will get affected quite considerably, and as a result this saddle point density will change. And it turns out that in this particular case the bulk distribution does not change, it still remains finite. What happens is that the charges which are there in this region, in this order 1 region, they all accumulate at the wall. As a result, now the new saddle point density becomes this. You have a piece of uniform part which is 1 over 4 alpha, and you have a delta function. So we can compute this density, and this density will be this is the configuration which will contribute most in this integral, and one can find out this partition function, and then as a result you can compute q as well. And what we find is that this is actually given by e to the power minus n cube and modulation function, which is the large deviation function, and this function is given explicitly by this, and at around 2 alpha this function also goes to 0 as a cubic power. It is quite easy to understand why there is an n cube in the exponent, as follows. See, so to bring this infinite barrier to this position, you have to push all the particles. So you have to have a energy cost, and the energy cost will basically, when you compute the partition function, that will give you that will be dominated by the energy cost. And if you estimate the energy cost, you are displacing the charges by order 1. If you look at these quantities and these x's are order 1, you can see that this quantity will be of order n cube, because there is this sum which is 1 to n, and this will be of n square. So this is of order n cube, and of course this order n cube charge order n cube energy is modulated by this function, because when if you just put the wall here, you should not have this energy, it should be 0. So this is modulated by this function, and we get this function, and this function goes to 0 as a cubic power. Okay, so this describes the probability when you restrict the position of the rightmost particle at order 1 distance away from the mean position on the left side. Now, what about on the right side? So in this case, we ask the question, what is the probability of observing this event that the rightmost particle is at order 1 distance away from this mean position on the right side? So basically, you put the x max here, and you ask what is the probability of such a configuration. And once again, you can compute this from this kind of probabilities. So it turns out that it is convenient to ask this probability here. Earlier, we were looking at probability of x max less than w, but here it is convenient to look at x max greater than or equal to w. And as a result, you have this difference in the numerator, and you can compute, and you see that the w comes in the numerator. And in this integral, the configuration which will contribute most is the following. It's basically that you basically take the rightmost charge and place it here, while all other charges are happily sitting inside this C. And the energy cost to pull one charge from this C and place it here will basically give you the order of this integral, and you have to find out the order of this energy cost for pulling this charge, and you can compute it very easily, and you see that this will be of order n square and multiplied by a large deviation function, and one can compute this large deviation function, and it grows it goes to 0 around 2 alpha as a quadratic fashion. So this is the kind of summary of the results, that in the 1D Coulomb gas, in the n going to infinity, the charges settle over a finite region, and the density is flat. And if you look at the fluctuation of the position of the rightmost particle, then it fluctuates. The typical fluctuation of the position of the rightmost particle is of order 1 over n, and these typical fluctuations are described by some scaling distribution which is not given by Tessier-Ulam distribution, but a different distribution. And the large deviation functions can be described by large deviation probabilities can be described by appropriate large deviation functions. And the behavior of these large deviation functions and on this side and this side smoothly match with the tails of this distribution. Okay, so this was the kind of question, the answer to the question which I had stated earlier. But in this case, we have also looked at other quantities which I do not have time to discuss. We have looked at the gap between the rightmost particle and the next rightmost particle, and we have looked at the fluctuation of this gap. And we find that this gap also has typical fluctuations of order 1 over n, and these typical fluctuations can be described by some scaling for distribution. We can compute this scaling distribution, as well as we can compute the large deviation probabilities also. And we have also looked at different quantity, which is the index, which is basically the number of particles on the positive side. So on an average, there will be n by 2 particles on this side and n by 2 particles, but the number of particles on this side will fluctuate, and we have looked at this quantity also, and it also has interesting scaling distributions that we have looked at. Okay, so there are some few open questions that we are looking at. So this in the beginning, I started with the log gas where the particles are interacting via logarithmic interaction. Then I said that if we change the interaction, and we considered 1D Coulomb interaction, which is mod potential. But what happens if we look at a more general interactions like this, and this kind of general interaction actually takes both the situation, log gas situation and the 1D Coulomb gas. For example, if you take k going to 0 limit, this interaction will give you logarithmic interaction, whereas if you take k going to -1, it will give you the 1D Coulomb gas. So is it possible to say something for general k to these kind of questions? That is kind of questions that we are studying in the future. Okay, so thank you for your attention and staying in the last talk. And I will also like to thank the organizers on behalf of all the speakers and all the participants. So I'll take questions now. No, k equal to 2 will be more.
No, like k equal to 2.
K equal to 2 is a k equal to minus 2.
Sorry, k equal to, no, I was thinking of k2.
K equal to 2 plus 2.
Yeah.
K equal to plus 2 is shortage interaction, so it will not be able to give you a y distribution. All the charges will kind of.
I think k equal to 2 still gives you.
Okay, let me think. K equal to 2 is very shortage interaction.
But it still gives you, I think, semicircle.
No, I don't think k equal to 2 gives. You have to exclude. No, it doesn't give. No, it doesn't give. Yeah. Okay, so if you, you don't need to put n square here. You can put something else also. Okay, and basically then you will have a typical scale of these positions of these particles, and which will depend on n. So you can actually scale axis by this typical scale, and you will get some independent constants here. No, that's what I'm saying. You don't have to. You can put constants here.
Yeah, but if you take n to infinity, everything will shrink.
No, that's in the n going to infinity limit. You have limiting distribution. You have to rescale. It's not an assumption.
N goes to infinity just means that the potential energy is very strong.
No. This will also have. This can also have. You have to compare this energy with this energy.
Okay, so also the V depends on n.
Yeah. Yeah, I just copied the earlier expression and changed that interaction to V. So yeah. You should look at the probably earlier expressions. Yeah. For example, here you have n square. Here you have n.
Okay. No more questions. I'll just repeat the vote of thanks and thank all speakers, and in particular David and Gregory, for a fascinating and varied conference.
Okay. So to close this one-week meeting, again, I would like to thank all of you for coming here. I'm not going to summarize all the diversity of talks. You have appreciated this. And again, I think it would be great that in 1 or 2 years from now, something like this repeat, so that we get all together at some point in the future. Thank you very much. Bye.